Okay. Now I am taking the u, suppose the height is 1, okay, and this value is 0, the height of the value of this function at 0, 0 here. Now u is an unknown, values are here. Now according to the value it moves. Here value is 1, this portion moves with a speed 1, this point moves with a speed 0 because its value is 0. The solution u at the time t is equal to 0 is u. This is the u. U is the speed. Therefore, this portion moves with a speed 1. This doesn't move at all because speed is 0. Therefore, after some time t, what happens? This moves faster than these parts. Therefore, the value will be like here. Because this is fixed, this portion doesn't move at all. Okay? Then what happens? Mathematically it is meaningless. For example, if you want to find a solution at this point, is a multiple load. The value of this point x naught, the function takes 2 values. Okay? It is a multiple valued, not a continuous function. Okay. So this the shape got changed. Shape got changed because it is a non-linearity. Okay. For example, you take a water on a table, put some water on a table, and you start to spread in a normal directions. So after some time, shape may get changed. You know, the boundary of the shape will get changed. It is a non-linear phenomena. If spreads uniformly, then it is a linear phenomena. Okay. So that is why the solutions may not be even a continuous. Therefore, we have to think of that usual weak formulation is, we have to look at it. What is the weak formulation? So if the system is in the divergence form, I can do the integration by parts. For example, I take the simplest example, ut plus of f of ux is equal to 0. Suppose if I assume the u is smooth, then after some time t, I will have a problem. Okay. To avoid this, so I will consider this equation doesn't satisfy because solution not even a continuous function, because at this point, so I have to, what I am doing is that do the integration by parts. Minus infinity to infinity, multiply this function v. V is a function in t and x. It has a compact support. Outside of a compact set, v vanishes. Outside of a compact set, such a function. Okay. So I am multiplying this v, then do the integration by parts. Then what happens? U into vt plus minus plus f of u into vx. Okay, integration by parts, dx plus, here after time t the function vanishes when I do the 0 to t here. So this will become minus infinity to infinity, ux is also minus sign, u of x 0, v of x 0, dx is equal to 0, integration by parts. So the integration by parts, what is the useful here? So the derivative is shifted. So that is what the beauty of the integration by parts is, this one, u dash of v is equal to minus of v into v dash of u, isn't it? The derivative on this one, u dash, is shifted to the another function with that. So now u is relaxed from the differentiation. Okay, there is no derivative on u. Therefore, whenever u is smooth, both are equal. Otherwise, they are different. So instead of this one, I consider this one here. So u is need not be continuous now, not even continuous. Even it can be integrable. That is enough. We take in the sense of Lebesgue integration. Therefore, my equivalent relation becomes as the integral 0 to infinity minus infinity to infinity u vt plus f of u vx, okay, plus minus sign I will get it because it is equal to 0. Therefore, minus infinity to infinity f u of x 0 v of x 0 dx is equal to 0. So, studying that PDE ut plus f of ux is equal to 0, weak formulation. Since u is not differentiable, then I have to go to this formula. Okay. Instead of studying this equation, because this formula does not require u, even u need not be a continuous function. By Lebesgue integration, it is a bounded measurable function, it is enough. Okay. Any bounded measurable function is Lebesgue integrable on a compact set. Because I am taking the v vanishes outside of a compact set. Therefore, this integral also vanishes outside of a compact set. Therefore, it is fine. Okay. Now, but if I write in this fashion, I have a difficulty to understand this. It looks, this is much more complicated than this. If I do the integration terms and so on. So, now suppose assume that the sum, what happens across the discontinuity. The left value is say that at a point across a curve C is given by xt. Okay. The function is discontinuous. What happens across that curve I am interested to study here. UL left value, say UR on the right hand side. Okay. When I say that the function is discontinuous, the left value is UL and the right value is UR, but for mathematicians there is a difficulty. What is the guarantee that limit exits? We have two kinds of discontinuities, the first kind and the second kind. Okay. First kind means left and the right limit exits, the function is not continuous. Second is no limit existing. Okay. So, now the question is that what is the guarantee that left and the right limit exits? I say that solution is discontinuous, but I have to classify now whether it is a first kind or a second kind. So, how to understand this one? That is a difficulty, because when I say that left value is UL and the right side is UR, what is the guarantee that limit exits? For physicists or engineer, they will just take it, but for mathematicians to write every step, we have a difficulty. So, what I will do is that, have you studied the functions of bounded variation? Anyone? Students studied the functions of bounded variation. F is function of bounded variation if and only if. What is the theorem? MSc students, everyone must be knowing. Huh? If and only if. Huh? Tell me. It can be written as a difference of two monotone functions. Okay. If it is a monotone function, left and the right limit exits. It assures you. So, the mathematical theory of the conservation law says that discontinuity is not bad. It is discontinuous, but the discontinuity is not bad. What it says is that theoretically one can prove that if your initial data u of x0 is in the BV functions of bounded variation, in the case of a scalar conservation laws, solution is also in the functions of bounded variation. Therefore, it can be written as the difference of two monotone functions. That is one of the very crucial result in the functions of bounded variation. A function is of bounded variation if and only if it can be written as the difference of two monotone functions. Monotone functions left and the right limit almost exits. Okay. Therefore, the solutions of the conservation law has a limit. So, left and the right. Therefore, I can speak of the left and the right limit here. I take now the solution, initial data is in the functions of bounded variation. Once I get this one, so now what is the across this one, what is the condition? It cannot be differentiable. This PD cannot be satisfying and the function is not even continuous. This cannot be satisfied. but across which instead of PDE, it satisfies this condition, f of UL minus f of UR is equal to the curve x dash t into UL minus UR. This is something like a mean value theorem. Okay, Rankine-Huygens condition is something like a mean value theorem because it is discontinuous. F of B minus f of A is equal to f dash of Z naught into B minus A. Okay, F is smooth. So this is something coincides with the f dash of Z naught. So this PD, suppose I took that ut plus f of ux, when the solution is smooth, this can be written as the ut plus of f dash of u into ux is equal to 0. Okay, when it is smooth. So this x dash t, something by the mean value theorem corresponding to some f dash of Z naught. Okay, this is usually called the Rankine-Huygens condition. Rankine-Huygens condition. Okay. So if you remember the mean value theorem, you can easy to remember the Rankine-Huygens condition. F of UL minus f of UR is equal to something that coincides with the x dash t, speed of the discontinuity. This curve f dash of Z naught is replaced by x dash of t. Okay, this form. Suppose the function is continuous, equality holds. F of UL becomes f of UR and the equality holds. So now already that some Ratan must have told that. So across the discontinuity, it does not satisfy the differential equation, but it satisfies this jump condition. It is very clear now. Jump condition. Okay. So it's a PD, it satisfies this condition. Now he must have already given an example that when the satisfies the weak solutions, solution may not be unique. I think he has done it already. The solution is need not be unique. Solution is need not be unique. Okay. He must have given this example. Now I am not going to the proof. The proof is I have given in my notes. You just go through it. It is not complicated because I give that important key points so that it is not available in other textbooks. Okay, so that where you can learn more. The remaining mathematical technical part you can always read in my notes, but I am giving the crucial steps. The solution may not be unique. So what to do? Now this is the statement of my PDE is the first law of thermodynamics. I told that neither energy can be created nor can be destroyed when there is no energy goes outside of the universe or no energy comes inside. This is a general form of that statement. Now what to do? Now I have to fix the uniqueness. So when you have a difficulty, what we will do? We don't know how to assumptions we should make it. Then we will go back where this problem has come from. Okay, why, where, what is the difficulty there? So now we will move to the second law of thermodynamics. Okay, that says entropy. Okay, this is I have forgotten the name. Suddenly it is not coming to my mouth. After that I will tell you. En means an energy. Tropy means change in an energy. Okay, there is a word coined by who is responsible for second law of thermodynamics. Okay, I will tell you later. So this is a word coined by him purposefully. He tells that why he has coined that word. Energy, for example, happens. You will see huge amount of energy. Within a fraction of a second, you don't know where that energy has gone. Isn't it? Heavy lightning, you see it within a fraction of a second, you don't see anything. That means nature taking care very well. Suppose that energy remains for some time. What happens? Things would have been burnt because of the huge amount of energy. But nature takes care that it jumps to the zeroth level. It spreads throughout the universe, but total energy in the universe remains the constant. But it spreads in such a way that means energy always jumps from higher level to the lower level. Okay, energy always jumps from a higher level to the lower level. If there is a discontinuity in an energy, left side should be higher than the right side. If there is a graph of an energy, left side should always jumps from higher level to the lower level. It's a natural phenomena. Okay, no energy jumps from lower level to in the universe, all the energy don't come and jumps up. No, that is not possible. The nature prevents it. Lower energy cannot, all the energy in the universe cannot come together and jumps at a point. No, that is not possible, because nature has to maintain the stability of the thing. Okay, always jumps from the higher level. If there is something goes wrong, immediately it shut down it. That is the nature is preventing us. So if there is a thing, energy means f of u should be convex function, something like a kinetic energy, mv square by 2, half of mv square by 2, no? So half of mv square, m you take 1. So energy, that if f is a convex, we can generalize, mathematicians have generalized it. If f is a convex, f is convex, then left side value is greater than right side value, then we can prove the uniqueness. They prove the uniqueness. If f is convex, so it's a natural phenomena. Left jumps, if it's an energy, this result should happen. Suppose if it is not an energy, okay, then if it is not a convex function, how to generalize it this condition? Okay, Volenic condition. So this gives that the entropy, the word gives you that should be jump from higher level to the lower level, and mathematician generalizes it, whatever may be the f. Okay, it is a mass, momentum. There the jump need not be from the higher level to the lower level. Okay, so she gave the mathematical condition and proved the uniqueness in the following way. Suppose the left value f of v minus f of ul is v minus ul, u minus ul should be greater than or equal to x dash of t, that is the speed of the discontinuity. There is a xt curve across which there is a discontinuity. This speed x dash t represents the slope of that curve, represents the speed. Always the slope represents the speed. Okay, it should be greater than or equal to f of v minus f of ul, sorry, f of ur, right side value, v minus ur for all v between ul and ur. Suppose if there is a discontinuity, it may be like, need not be like this, it may be a discontinuity of this kind, also may be possible. Whatever may be the discontinuity, this should satisfy in this condition. In the convex case, it goes back to this condition. If f is convex, it is an equivalent to saying f dash of ul is greater than f dash of ur. Here v going to ul, it becomes f dash of ul, this is f dash of ur. Okay, in the convex case, but practically it is difficult to check it again. for all v. So you find you do computation. We do the computations, some numerical scheme. You compute a discontinuity. You don't know whether the discontinuity satisfies entropy condition or not. This inequality. Okay. Here I classify again. When f is a linear function, what happens? F of u is equal to u. This is 1. This is also 1. Strictly equality holds. Okay. Equality holds. F of u is equal to u. F of u is equal to u. Equality holds. So there are two kinds of discontinuity. Equality may hold. If f of u is convex, f is convex, strict inequality holds, because f dash of ul is greater than f dash of ur. Strict inequality holds. I classify the discontinuity, okay, as a, if there is a strict inequality holds, for all v, then that discontinuity is called shock. I classify the discontinuity. But there is a linear discontinuity is also possible if you take the initial data. Okay. Therefore, if f is a non-convex function, some point it may equality holds. For some v it may equality holds. Some v it may not hold. But whenever equality holds, it is acting like a linear function. Okay. Therefore, if somewhere equality holds, that discontinuity is called, contact discontinuity. Contact discontinuity. Okay. So there are, I classified the two kinds of discontinuity. One is a shock, that is, if f is a convex function, the discontinuity is always shocks. There is no equality because of the strict inequality holds. If f is, there is no contact discontinuity. For example, f double prime vanishes somewhere. Strictly convex means f double prime doesn't vanishes. F double prime vanishes at some point means somewhere something like a linear function behaves like a linear function around of it. That is why sometimes it is also called linear discontinuity or a contact discontinuity. One portion is a linear and one portion. So I would like to explain what exactly the difference is. Okay. Now let us back to the theoretical part. So what is really happening? Let us try to understand. That mathematician Clausius, entropy. The entropy word is coined by this Clausius, second law of thermodynamics. That is a statement of him. He introduced the word entropy, coined by him. Okay. From the physics point of view, after that mathematician generalized it. Okay. For any function f, he did it for energy functional. Clausius definition. So now let us try to understand. If it is a linear problem, now what is exactly the difference between a shock, the contact discontinuity, and the linear discontinuity? What happens? The solution at a point x, suppose I am interested in ut plus ux is equal to 0. Okay, let us try to understand what is going on. Suppose the solution is given by, suppose you want to find a solution at a point xt. So by our definition, u of xt is equal to u naught of x minus ct. You could draw a curve, it touches a point x naught. This curve is given by, slope is given by dx by dt is equal to 1. Coefficient is 1. Okay. The solution is constant along this line, isn't it? That is what you must have explained. Along the characteristic, the solution is constant. Therefore, suppose the initial data at time t is equal to 0 is given, f of x is given, then the solution here, they move parallelly. Let us try to understand what is the difficulty here. Parallelly, suppose at a time t is equal to 0, you is given a data and you allow it to move up. Now open the box, then it started to move up. It cannot move arbitrarily. While moving, it should satisfy this PDE. It is moving up and moving up in such a way that arbitrarily it won't move up. Informations at a time t is equal to 0 is information is given to you and you are allowed to come up. It started to move up, but while moving, it should satisfy the PDE. That means all the informations moves parallelly. All the informations moves parallelly. Okay, in the linear problem, the informations moves parallelly. No information is hitting each other. No information is hitting each other. Okay, because the slope of this curve dx by dt is equal to c. So dt by dx in the xt plane is equal to 1 by c. Okay, so all the informations moves parallelly. There is no danger, because whenever you want to know the solution, then you come with the speed of the line 1 by c slope. Sorry, dx dt by dx is 1 by c. Come with a still less than 0. F of x is equal to 0 if x positive. Okay. Now, what happens? I will consider this one, ut plus u into ux is equal to 0. Now, you need you here on the board is equal to 0. What happens here? The characteristic curve, the x dash t is equal to, I wrote that, this becomes dx by dt, that is a f dash of 1, that is the 1. Therefore, the characteristic looks like here with a slope 1. So, goes here with they are parallel again 1. Now, this data here 0, dx by dt x dash t is 0. Means in the xt plane, therefore dt by dx is infinity. Slope with infinity, they will be here, like here, the characteristic curve. Again, the solutions is constant on the each line, same argument. So now you come here, they intersect. The information from this portion, they hit each other. So till then, my solution is valid. It is up to here, it is a single value, up to some single value. Okay. After that, it becomes a multiple value. Now my question is, by weak formulation, okay, weak formulation is extended. Next, after t is equal to 1 maybe, after that it is not defined, it is multiple valued. Now I have to define here. Left side is 1 and the right side is 0. Okay. So in such a way that Rankine condition should be satisfied. So f of 1 is half, because f of u, sorry, I am taking u square by 2, that is ut into ux, that is f of u is equal to u square by 2, that is f of 1 minus 0, f of ul, one side is that one, 0 is equal to half into 1 minus 0. This implies the speed is x dash t is equal to half. So the curve with a slope dx by dt is equal to x dash t is equal to half. This curve will be there, and this side along which this satisfies. So now the curve will be moving. Now after that, it moves. After this, the discontinuity after this one, it moves like here. The characteristics comes left side 1 by, it will be like here. that line of discontinuity across which this side is 1, this side is 0, they will move like here. They move like here. So this is a shock. Because it's f is a convex function, it is a shock. Means the information enters the shock. This solution don't enter this region. This solution don't enter this region. Shock sucks the information. It won't allow to move to other side. They don't allow it to hit both the informations. There will be a shock will be created. The information from the left as well as the right, it sucks it. Okay, and moves it. That's why it's called a shock. Sometimes this may happen. Contact discontinuity means this is the line of discontinuity xt. This side, the line may be parallel. One side it may be linear. Other side it may be a discontinuity. Information comes from the left, okay, and hits this discontinuity, and this will suck the value. It won't allow to move out. So this information's right hand side moves parallelly. So this is the linear part, like moves parallelly. One side it moves parallelly, another side merges with this one. Then it is called the contact discontinuity. Okay, if both the side information comes and hits the line of discontinuity, and the line of discontinuity absorb the information from both the side, then it is called a shock. Okay, so this is called the discontinuity about that one. Fine, but computationally I cannot check these mathematical theorems. Computationally we get some answer, we don't know whether it's an entropy solution or not. Okay, how to check it? So mathematician always, theory is one side and practical implementation is on another side. So always we have to find a trick or a mathematical method how to check it quickly. Suppose you find some discontinuity. Is the time is up? Okay, fine. So I am not going to give any technical proofs. I will give more informations like this. So if you go through the notes, if you have any difficulties, you can contact me by email or my mobile number, and you can fix my time and you can discuss with me. Okay. Now, suppose you find by the numerical method some answer, discontinuity. Discontinuity. You don't know whether it is correct or wrong. You have to check the entropy condition, whether it satisfies an entropy condition. Suppose the discontinuity case 1, UR is less than, UL is greater than UR. Okay, you know the value, there is a discontinuity, but mathematically difficult to verify it. Okay, because it's all the discrete values. Then what you do is that you take a graph UR, UL, you mark it on a x-axis. Okay, then you know the graph of f, you draw a graph of f, it will be here between UR and UL, f of u, you draw a graph, and it is like that. You draw a chord, it may touch the function. If the chord is above than the function, then it is rightly satisfying the entropy condition. If UR is less than UL, and draw a chord, join these two lines. Okay, join those two lines, just a straight line. And if your graph of f of u is completely less below it can touch below that chord, yes, your discontinuity is correct. Okay, suppose yes, it satisfies an entropy condition automatically. All these conditions are equivalent. Now suppose UL less than UR, then you draw a graph of f from here to here, join the graph, you draw a chord, and if the graph is above, then the discontinuity is correct, otherwise thing. So if f is a convex, this graph cannot be above than that, because UL has to be greater than UR. Okay, if f is convex, then graph should be below, because it's a convex function, below the chord. Therefore, this is valid. UR is less than UL is valid. Yes, it's an entropy condition. Graph should be like this. F is a concave, opposite. F double prime is negative, therefore, this valid. UL should be less than UR. UL should be less than UR if F is concave. F is concave. So, suppose in the convex function, same thing happens. For example, UL is less than UR, data is increasing. Then it cannot have a discontinuity. Suppose the initial data is continuous function and is an increasing function. If F is convex, even though data is discontinuous, but solution becomes continuous. Okay. So, let me back to the example. It will take 5 minutes more, because I wanted to complete it. So, let me come back to the example I gave, how the model can be done. So, now observe that model. I told that you take the water and oil. How I am doing the model here now? You got the information. If F is convex, that has to be done, otherwise its solution has to be continuous. So, now water height is 1, and here half a, at a point half, the solution U of x 0 is equal to 1 if x 0 less than x less than half, and 0 if half less than or equal to x less than 1 is my data. Here is an oil. Okay. Now I have to find what is ut plus f of ux, because it is conserved, mass is conserved, only it is rotating, but total amount of the fluid is same, isn't it? So, f of ux is equal to 0. What is f now? What is f? I have to find it now. Okay. So, step by step I will go. Let us do the observation. So, whenever it is moving, I told that when they remove the layer, then fluid started to move. That is the PD explains how it is moving. Okay. So, now only what I have to find, what is that f? It rotates correctly. So, now I told initial data is discontinuous. Water level is 1 and 0 here. If I know the water, oil is always above than the water, therefore, it is enough if I find the water level. Okay. I told that how it goes at a point half. Look at here very carefully. See, oil rotates. The water droplet here at the point half, at the height half, since it rotates, this oil drop does not move left side or right side. It is an axis point. Okay. It rotates. This water level comes down and increases here. So, it is a typical, for example, this is the way before this moves like this. Okay. So, the water droplet does not move at the point half. Okay, it rotates, only that point water drop will be there only. Therefore, the velocity of that one, f dash of the velocity of that one, u half, okay, that is the point, at half t is equal to 0. At this point half for any time t, but in the initial data is continuous, but the discontinuous, solution is continuous. Here UL greater than UR, left side value is greater than UR, and the solution is continuous. This cannot happen if F is convex. If UL is greater than UR, discontinuity is allowed in the solution. So, discontinuity is not allowed and continuity is coming. That means one information I got it. F is a concave function. The model function is concave function. Concave function. Okay. One information I have. Second information, this one you have. Two informations I have. Okay. And the solution is, after some time, it becomes linear. Okay. Linear. So in this case, the solutions were given by, this is called the rarefaction waves. In this case, as the solutions are given by f dash of u is linear. F of u, f of, at this point, f of u 0 1, f of u at this point, f of 0 t is equal to f of 1 minus u0 t. See, this downs, equivalently this side are rises. So this difference is nothing but this side. This 1 minus of this side is nothing but this side. Therefore, I am writing this one. What is the function? You have three conditions and f dash is linear. What is the possible function? Now you can immediately conclude that f of u is equal to u into 1 minus u. F of 1 minus u, no change, because maintains the height. And f dash half is 0. That is the only function. Uniquely it says that. So this is the function. Okay. So today for the computational example, you take this one with initial data, this one, and how it rotates different times. Once comes down and ups. Okay. So this is just of the basic of this conservation laws with examples. Without mathematical techniques I explained. In the next class I will go for the numerical schemes, how we develop it, what is the intuitions and so on. Okay, then I will stop it. Oh, mic is not working. Okay. Oh, that's the problem is okay.
Okay, this nice presentation from sir will continue after a tea break. Even I am also learning the things, because from starting sir has started from physical to how do you more formulate the equations. In that way also I did not think actually previously when I read the this conservation laws things. Okay, this nice tremendous presentation will continue. Talk will continue after the tea break. Okay, thank you.
So we can have the participants. No, it's always we always prefer if you have food and everything is the participant. You can talk at least. You come to know interact also. So in this talk, I am slowly moving to the numerics part of the how to do the computations. Okay, I will give only the basics, and again mathematical proofs you can see in my notes. What are the difficulties? What are the things? So sometimes we have a theory, existence, uniqueness, and so on, but practically it is impossible to compute it. It may not be possible. Simple examples I go ahead. Okay. So not only conservation laws, how the numerical analysis one has to study, why one has to study, why one has to study the numerical analysis with analysis. I am telling analysis and computations. Okay. I always give this example. We study in the +2. I start with that. So our job is now here not only developing an algorithm, how much cost I have to save on a computer, cost of the how much of time it takes. Okay, these are two. If it is a mathematical proof, whatever maybe it is a length or short, it doesn't matter. But when you come to a computation, the cost is very important here. How much of time it takes your algorithm to solve a problem. Okay, I always give this example, that is a inversion of a matrix. Ax is equal to b. I start with that. A is an n cross n matrix, B is a vector, Ax is equal to b. Theory Z says that if f is invertible, this has a unique solution. Theory is over. Okay, that is the A is invertible or determinant of A is not equal to 0 implies x is equal to A inverse b. Over, theory is over. Now the difficulty is I want to do the computation work. It's the simplest thing. We start with the computation with the solving linear systems. Okay. So in our +1 or +2 level, we study what is the how we will solve it. Some there is a famous rule, no? Cramer's rule. Cramer's rule. Cramer's rule. It gives the explicit solutions. Explicitly xi is this much. So for example, if A is the matrix A11, A1n, AN1, ANN, suppose if it is A, define AI by the ith column is replaced by B. Okay. Then each xi is given by determinant of AI divided by determinant of A. Determinant of A. Over. So simple and a beautiful, mathematically beautiful formula given by the Kramers. Okay. Now the question is mathematically settled, explicit formula is given. Today we have a supercomputers. 1 per second it does the billions of operations, addition and multiplication. We may think that yes, it is simple. But suppose if you take a 50 cross 50 matrix, full matrix, okay, and go via the Cramer's rule, how much of time it takes? At least 6 months it takes. I want for example, you are doing a weather prediction, you have a data today, all the practical problems, finally if you simplify it, finally reduces to the Ax is equal to b. It doesn't work. Suppose Cramer's rules have worked, you would have been, most of us would have been unemployed. Numerical analysis course becomes mild. Okay, why this happens? Can you guess? Those who teach us the numerical analysis course, what is the culprit here? Why it takes so much of time? Even though it's a mathematically, analytically, the solution. Everything is beautiful, fine, but nothing will work. The culprit is the determinant of a matrix A. So suppose how many terms will be there in the determinant of a matrix? For example, 2 cross 2 matrix A, B, C, D, answer is determinant of A is AD minus BC, there will be 2 terms. If it is 3 cross 3, how many terms will be there? 3 cross 3, 4 cross 4, So it has an n factorial terms. N factorial terms will be there. So if you want to invert a matrix by 50 cross 50, 50 factorial terms is not a small number. Even your supercomputers, that's too big number, it takes a huge amount of time. It's completely failed. Okay, that is why you started to study, I want to reduce the computational work. So the first method is the Gaussian elimination. That is the first method we study, is that when you don't know the matrix, whether it is a positive definite or anything, we study that takes how much of operations? N cube by 3 number of, it reduces tremendously. You look that where is n factorial when n is large, suppose n is 100, where is 100 factorial and n cube by 3. We are avoiding the determinant of a matrix. We want an algorithm on a computer. We should not find a, when you don't know about the properties of the matrices, don't, when the matrix is big, don't try to find the determinant of a matrix. Okay. So similar way in all the PDE problems, we have to give an algorithm. Okay, it consumes the time is less. It is not only proving mathematically convergence analysis and so on, everything is beautiful, but how much of time you are it takes. So that is one of the crucial step. So we are let us try to analyze our conservation laws. So we'll give different formulas. So which takes more time, which takes less, according to convenient you can go ahead. So now let me start with a ut plus f of ux is equal to 0. Okay, u represent my exact solution, v represents my approximate solution. Okay, so I will approximate u by an approximate solution on a very grid. Here, this is in time, one dimensional only I am doing, that is t is equal to 0. You must have known what is the finite difference method. We will just start with the finite difference method. In time, this delta t, time discretization. In the x direction, I will take this h, uniform h to start with. Okay. So now this is I am approximating at every point xi tn, xi comma tn. I will write this one as the u of I, okay, n, v of solution, exact solution at a point xi tn is nothing but u I n. Subscripts represent the variation in the space and the superscript represents the time. Okay, n. So this is my understanding. Okay. Now I will try to approximate this one. Vi of n plus 1 minus Vin by delta t. There is an approximation of the time. Ut, approximation of this one. Okay, forward in time. I am taking here. So here I wanted to approximate this one. Okay, but the solution is discontinuous. Like if the solution is continuous or something, I can do it. So that I will approximate some like here, n minus f of I minus half of n by h is equal to 0. So before going to do that, whenever the problem comes, don't attack nonlinear problem in the first. Whenever you develop something, whether it works for a linear problem or not, first try to understand that. If it works, then you analyze in your hand why it is working, analyze perfectly, and you enter to the nonlinear. It is easy to understand. Without checking the linear problem, don't do anything. So let me start with a conservation law differs from the elliptic and the parabolic equations. It doesn't care. You cannot, like in the parabolic or elliptic, higher order schemes are not possible. That is the main difficulty here. because of the, let me start. See, if you understand linear problem clearly, it is not difficult to understand a nonlinear problem. So, now let me start with a linear problem. ut plus ux is equal to 0. Here I will put that vin plus 1 minus vin ut plus c into ux. Okay, let me take it. Instead of fixing, I am varying it. C is equal to 1, that is come. Delta t plus ux I have to approximate it. Ux I have to approximate it. You can use the ux is approximated by ui plus 1 n minus uin by h. There are different ways you can approach. This is the forward difference, you are familiar, and uin minus ui minus 1 of n by h, backward difference. All are converging to ux only, isn't it? Or if you can use the central difference, ui plus 1 n minus u of I minus 1 of n by 2h, central difference, backward, and this is a forward. Which one I should use? Which one you should? Huh? No. As a layman, I don't know mathematics. Okay, I want to start. Can I use it all? Why? So, as a layman, I want the physics behind it. It is not the mathematics, of course, you put the mathematical technical, but what is the physics behind it? I would like to see it. Suppose if I start with a C is positive, C is positive, okay, then I will use the forward difference. What happens? ui plus 1 minus uin by h is equal to 0. Okay, it doesn't work. It doesn't work, but theoretically this converges to the ux. Theoretically it is fine. So, PDE, approximation of the PDE, this converges to this, because this converges to ut, this converges to ux. Approximation of the PDE converges to the PDE, but solution doesn't converge. Got it? Approximation of a PDE converges to the PDE, no doubt about it, because this goes to the ut, this goes to the ux, but solution does not converge. What went wrong? What went wrong? Why it is not working? Why? See, when C is positive, wave is moving from left to the right. When C is negative, wave is moving from the right to the left. When the moving wave is from left to the right, all the data is hidden in the left side, no information in the right side. Therefore, I should take the backward, because you want to compute the solution at the ui, because you have to back side, ui minus 1. The information is written in here, left side. When the wave is moving left to the right, all the information of the wave is in the left side, because the right side is empty, it is not yet moved at all. So, that is the information. So, the information is hidden in the left side. Therefore, if you take the right hand side, it is not working. Okay, why this is the thing? What is the theory? Mathematical theory says existence and uniqueness results. See, numerics is nothing to do, definitely if you understand theoretically existence and uniqueness. See, there are three types of difficulties. One, there is a physical problem comes. There are three steps: converting that one to the mathematics, that is called the modeling. Then theoretician enters there. Second step is this problem has an existence and the uniqueness of a solution. That is very important. Don't say that this is a pure mathematics and this is an applied mathematics, because how long the existence shows that how long this model is valid, for what conditions this model is valid, mathematically it is valid or not. If you prove existence, suppose if it has a more solutions, when you can get what is the condition on the solutions, you will get the physically meaningful solution. If suppose you have thousands of solutions, among that one is the real solution, how to go to that one? Then on the uniqueness proof you have to put some conditions. So what is the condition? That assumption should be relevant to your physics. So you are proving it. Okay. So existence and uniqueness is very much necessary, theoretical part. Once it is that, but the people who does the existence uniqueness, they don't know where that problem has come from. It is for them, it is a differential equation. They just prove it. Next, the third part is implementing on a computer, because theoretician existence uniqueness does not give the solution. It says that the solution is valid up to this interval. Again, the numerical analysis has to come now. Okay. If you understand properly the theory, can you go along with the theory? The numerical development is one choice. Okay. So otherwise there are two ways. One is from the physics, he can develop a numerical algorithm if he knows physics, and if he doesn't know the techniques of mathematics. If you know the existence and the uniqueness, so along the theory, first you develop a scheme, don't worry about the cost. Once you develop some numerical scheme, you are sure that it converges, then you start to reduce the computational time. First, one given a problem, first you check whether it has a correct numerical solution or not. After that only think of the reducing the computational side. Okay. So this clearly says that this one. So when you go to the why this is called, what is the difficulty, how it is related to the mathematics. While doing the deriving the solution, you never assumed that C is positive or C is negative. When doing the solving the ut plus ux is equal to 0, C into ux, in theory I never assumed that C is positive or negative. I got that solution. Why I was unable to doesn't have the difficulty there, and still I have a difficulty here. Okay. Is it not related to the theory? Yes, it is related to the theory. So let us to understand this one, let us go to the wave equation. This is also a wave equation. Okay. So you come to the wave equation, utt minus c square uxx is equal to 0. Okay. So that is why first what we do is that we study the basics of the PD, linear PD. This can be decomposed into del by del t minus c into del by del x, del by del t plus del u c into del u by del x is equal to 0. I am splitting here. Composition of two waves of the first order, minus c takes the wave to the forward to the backward, from the wave is moving from right to the left, plus c takes the part left to the right. Then what happens at every point? Moves forward, backward, forward, backward, forward, backward. That is why it represents the vibration of a string. Okay, it is a composition of two waves. This is the first order PDE, it takes to the right side. Okay, sorry, left side when C is positive. This takes to the right side, left to the right. Therefore, left, right, left, right, left, right. It is a vibration. When the wave is moving, it vibrates and moves. Okay. So here we know the explicit solutions. That is called the, first you try to that whenever the wave comes, first try to understand this D'Alembert's equation, what is happening. Okay. So explicitly is given by, suppose the initial data ux0 is equal to f of x, ut of x0 is equal to g of x. Okay. Then the D'Alembert solution is given by u of xt is equal to f of x plus ct plus f of x minus ct divided by 2 plus 1 by 2c integral of x minus ct to x plus ct to zz dz. Okay. So what is the domain of dependence? Domain of dependence. What is that? If you want to find a solution xt, okay, what is the domain of dependence? It depends on the x plus ct, x minus ct, the interval x minus ct to x plus ct. Therefore, you should know the data from the point x minus ct to x plus ct. Initial data, if you want to find it, so this is the curve x minus x plus ct. Okay. If you want to find a solution, you should know the data from here to here. The solution is defined in this one. This is called the domain of dependence. Domain of dependence. Okay. Means if you want to find a solution, you observe it here. If you want to find a solution at this point, you should know the data. If you miss a little bit data, you don't get a solution. Clear? So when you develop a numerical scheme, numerical domain of dependence, suppose you insert a numerical scheme on this one in the t and x variable, your numerical domain should be bigger than this. Numerical domain, you should also find the xi, that is at the uin, depends upon the initial data. Okay, it computing this one, I use this one to compute this one, I am coming down. Okay, so I am coming here. So numerical domain should be bigger than the theoretical domain. Okay, numerical domain should contains always the theoretical domain. That means you have all the data. So that is the stability condition, that is the CFL condition. Whenever the numerical domain contains the theoretical domain, first it is observed by Courant, Friedrich and Levy. So they that numerical domain should be bigger than the theoretical domain. That means your numerical domain contains all the data, you are not missing any data. That means it is working. That is it from the point of physics. So when you are doing mathematically, I am going to put a condition now. Numerical domain should be these slopes. Suppose if I draw this slope, our numerical domain slope should be smaller than this one. So that restricts that c into delta t over h less than or equal to 1. Okay, this shows that. So it is not that CFL condition is coming. Theoretically it is coming. It is the theory. In the wave equation, what you study? Domain of dependence and the domain of influence. Okay, when you study the D'Alembert solutions, immediately we go that we study what is the domain of dependence, why we are studying. That is very important from the numerical point of view. When you develop a numerical scheme, suppose if in implicit schemes, then it always contains the domain of dependence, but it is a waste of time from the point of this one. So here, note here that too much numerical domain is too much big, it contains that, then also solutions may not be good, implicit schemes. Okay, when they given a problem, what method I should use? See, before going to any the things, okay, you prove the results and so on, stability, convergence analysis. But given a problem, PDE, first you classify it: elliptic, hyperbolic and parabolic. Okay. So once it is classified, what schemes I should use? Finite difference, that is okay, that is different. Finite volume, finite and so on. Whether I have to use the explicit or implicit. Okay. Whenever the hyperbolic equation comes, using an implicit scheme is a waste of time. You don't get the good accuracy. Why? Whenever a parabolic scheme comes, Crank-Nicolson scheme is the better. You feel that. Why it should be better? When an elliptic equation, of course, it is not depending on the time, so always it is an implicit, so there is no problem. Okay. Why in the time dependent problem like the parabolic or hyperbolic equations, what scheme I should use? Finite difference or implicit scheme or explicit schemes? Okay. Now let us try to understand the physics here. So this is what I am telling these classes rather than proving the mathematics. Okay. So why I should use, what scheme I should use, explicit or implicit? So now let us come to the heat equation. Heat equation. That is why I am telling, before going to any problem, nonlinear problem, try to understand the linear problem first and what is going on the linear problem. And if you understand clearly depth of the linear problem, you can understand the thing. Now let us try to consider the heat equation. What is the difference between the heat equation and the wave equation? Both are time dependent. Both are time dependent, isn't it? So now, okay, let us understand the first order. Ut is equal to uxx. This is the heat equation. And the ut plus ux is equal to 0. It is a wave equation. The wave equation means it is a one-sided wave equation. Waves move from left to right. There is no vibration. When you take a second order wave equation, that is a vibration. I told that it is a composition of the opposite signs of the first order PDE. Okay. So now this is u of x0 is equal to f of x. So the solution is given by u of xt is equal to u naught, I will take c here, x minus ct. Even if you want to take c is equal to 1, it does not matter. Okay. Now compute the solution of this one. What is this? U of xt is equal to 1 by square root of 4 pi t, something minus infinity to infinity, u to the power of, this is how the solution of the heat equation now, u to the power of minus something x minus y square by 4t, something like that, f of x dx. F of x dx, f of x is equal to f of x dx. What is the difference now between the heat and the wave equation? Look, the solution is u naught of x minus ct. Here the integration. Here what is the domain of dependence? What is the domain of dependence? What is the speed of a heat equation? What is the speed of a heat? In what speed it moves? Anybody knows? See, that is I know that wave moves with a speed c. In what speed heat moves? Okay. Now let us try to understand this formula is correct. Okay, this correct formula is correct. Now I will take a rod. Okay, and at the point x0, I will just put a candle, heat it, and take it out. Okay, so my heat in the initially minus epsilon epsilon. So my initial data f of x is equal to, say heat is 1, I put it heat 1, slowly it will be like here, graph, because at the point and it will be like here. Let us assume epsilon, some curve, positive curve. Okay, so that is, I will call it as some positive c naught. Okay, in the interval minus epsilon to epsilon. For the time being, I will take 1 and 0 outside. Okay, at that point. Then you put it here, then this integral reduces to 1 by 4t into minus infinity to infinity e to the power of minus something, and that is the value. Therefore, since that function vanishes, minus epsilon to epsilon and u naught of x dx. U naught of x has a compact support outside of a compact interval. My initial condition, just I will put it and remove it. So immediately on that spot there is a heat, and immediately heat is vanished at a time t is equal to 0. There is no other part. Now what happens? T is equal to 0 is equal to, this is the situation, t is equal to say t naught plus epsilon, very small time. Okay, now what happens? This gives initial data has a compact support, solution does not have a compact support. This is always strictly positive. Okay, the heat was 0 at the initial stage, heat was 0, but when you, for any epsilon positive, heat is spread throughout the minus infinity to infinity. What is the speed now? In a fraction of a second, it spreads over minus infinity to infinity. The speed of the heat is infinity. The speed of the heat moves in a speed of infinity. You understood that? Because Here only it is outside, it is 0. In a fraction of a second, it spreads because of this. Look that for any xt, this is positive. Sheet is positive, and as long as t is positive, that shows that it's minus infinity, it is positive. That shows that it moves in a infinite speed. So what is the domain of dependence? You compute it. Domain of dependence should be contains the theoretical domain of dependence. Therefore, the numerical scheme it should contains bigger domain of dependence. That means implicit schemes are better for the heat equation. Okay, that is why second order scheme, practical schemes are better. For parabolic equations, it is better mix with an implicit part. Don't go explicit part. Then what happens to the linear equation? The solution at a point xt depends upon only one point, nothing to do outside. Okay. Domain of dependence is small even for any time t. Okay, you need not to go look for the bigger domain of dependence. Only theoretical domain contains. Theoretical domain is a finite set. For example, wave equation domain of dependence is x minus ct to x plus ct. So it is enough if I have the data this much. I need not have data up to minus infinity to infinity. Too much data if I have it. So it gives the explicit schemes are better for the wave equation. Okay, because so what is the definition of mathematics? How do you define? If initial data has a compact support, no. If initial data has a compact support, and solution also has a compact support, then it moves in a finite speed of propagation. That is called the finite speed of propagation. Waves moves in a, how do you mathematically, you have to define for everything. When the initial data has a compact support, the solution also has a compact support. So that is why in the wave equation we study the domain of influence. Okay, suppose if your data has a compact support, then at any time t, the solution only will be inside of this. This is called the domain of influence. Okay, therefore domain of influence is always has a compact set. If this is a compact set, it is multiplied by, if it is a x is here, x plus ct will be here. Okay, some increases, but still it has a compact support. Therefore, for the wave equation, if the initial data is compact, for any fixed time t, solution is also has a compact support. There is no going up to the implicit scheme minus infinity to infinity. Therefore, explicit nature is better. Okay, if it is a parabolic equation, because it moves in a speed infinity, heat equation is the model. For us, the conservation law wave equation is the model. So that is how, this is how we determine first. So I move to the explicit schemes. You understood that why? Given a PDE, you should see parabolic, hyperbolic, and this one, according to that you have to use the schemes. So now another difficulty is here, we are facing it here. Numerical schemes depend upon the Taylor series. Understood? Numerical schemes, it's time over. It's not over. Okay, fine. No, I am just asking you when the time is over. Again, you tell me some 10 minutes before. So this is how the domain of dependence, and this one it comes. Now I will start with the numerical methods for my conservation laws. So ui of n plus 1, my numerical scheme will be vi of n plus 1 minus vin by delta t plus some flux. This is the approximation of the flux function f of u. F of u is approximated by minus f of I minus half of n by h is equal to 0. How to find f? Because we don't know wave is moving from left to the right or right to the left. You should choose forward or backward according to that, isn't it? So assume that you have done that. So here this is can be written as the, I am rewriting as VIN plus 1 is equal to VIN plus delta T over H minus sign will come. Minus sign this one f of I plus half n minus f of I minus half of n. This is approximation of the, it chooses forward or backward, I don't know, that is why. So f is depend upon, okay, suppose it depends upon the finite speed of propagation. Suppose if it is VIN, we go up to VI minus k and I plus k here, and the n plus 1 solution I want to compute it. I use that n plus 1 data and computing the solution at a point t. Okay. So now, see here, when you are doing these problems, I am computing, you know, the solution at the t equals Tn and computing a solution at the Tn plus 1. Okay. Always I know today I am computing the day solution tomorrow. That means nature allows you in only one direction. Means from today I can move to the tomorrow, I cannot go back to yesterday. Okay. Why it is not possible? Nature maintains the entropy condition. Irreversible phenomena. Is the time the evolving is an irreversible phenomena, nature maintains it. Suppose if it is not maintained, somebody will go to yesterday, somebody will go to the tomorrow, like that. Universe becomes unstable. To maintain the stability, the universe maintains you always moves in the forward in time. It won't allow you to go to the backward. So conservation laws, that the discontinuous solution, you know that the solution at the point t equals Tn, you can compute the solution at the t equals Tn plus 1, you cannot compute a solution to Tn minus 1. By knowing the data today, I can move to the forward, I cannot go to the backward. How to explain mathematically this irreversible phenomena? How to explain? I cannot go back, but only I can move forward. How to explain mathematically? So this is the one people struggled, because one side physics is growing. Mathematicians have to supply equivalent to the physics. Okay. In 1950s, functional analysis, to understand this physical phenomena, functional analysis started to grow. Okay. Why? Then how do you explain this one physical phenomena? In 1950s, people were able to come up with a good explanation. The solution of the hyperbolic conservation laws, u of xt can be put as the st of u naught. St is an operator taking the initial data to the time t. They prove that st is a semi-group. St is a semi-group, it is not a group. It does not have an inverse. In other words, they were able to say that S is a compact operator. S is a compact operator. You may not be knowing what is an S is a compact operator. S is a compact operator means, see, you have a bounded sequence. In Rn, you know that every bounded sequence has a convergent subsequence. Okay, Bolzano-Weierstrass theorem. But when you go to the infinite dimensional, that result fails. That result fails, isn't it? I cannot use, because I am looking the solution in the L infinity class or BB class, they are all infinite dimensional space. Even though solution is bounded, numerical solution, approximate solution is bounded, I am not sure it has a convergent subsequence. It converges. I do not need a mathematical theory, but yes, if it is a compact operator, okay, if un is a bounded sequence, un is a bounded sequence, then S of un has a convergent subsequence. Convergent subsequence. It takes the bounded sequence to the convergent subsequence. We call it as VAN. Okay. This compact operator does not have an inverse. It is a continuous function. Inverse is not continuous. It's a compact operator. Inverse, you understand that what is a compact operator? It takes the bounded sequence to the convergent subsequence. Okay, Vn is S of Un is bounded only, that need not to converge. For example, -1 to the power of n, it is just a bounded, but still it has a convergent subsequence, -1 plus 1 subsequence. In infinite dimensional spaces, we may not be having. Okay, that is a nice exercise to do it. So, what happens? Suppose inverse is continuous. What would have happened? Identity map S is inverse is also continuous. S is a compact, S inverse is continuous, then implies identity map is a compact operator. Okay. So, what happens? It takes the unit ball. Unit is a bounded set. Unit ball is a bounded set. S of u, suppose if it is an inverse, then it would have taken the S of u is again a relatively compact. U is bounded. S of u has a convergent subsequence. S of u has a relatively compact. Okay, because S is a compact operator. That has a convergent sequence. That means once it is a compact operator, again it is bounded. But unit ball is bounded only where? It is closed and bounded. Compactness equivalent to closed and bounded only in the finite dimensional. Infinite dimensional, that result is not true. Therefore, S inverse cannot be continuous. Otherwise, identity map becomes the compact operator. If S inverse is if it is reversible, yes, you are going there and you are coming back, then identity map becomes the compact operator. That is wrong. Then unit ball is compact in an infinite dimensional space, then it is a contradiction. Therefore, this represents the thing. So, hyperbolic equation is always irreversible if it is non-linear. Okay, only you can go Tn is data, Tn plus 1 is known. Except in the linear problem, solution at the point xt is given by the same reversible. The linear case, solution at the x naught. Along the characteristic, you can come down and you find the initial data. Suppose I am moving tomorrow, I cannot trace back the yesterday from where I have started, because two different data after some time t, they have the same solution. Okay, two different data after some time t, they may have the same solution. You cannot trace back which data have come from. But in the linear case, that does not happen because they move parallelly. Two different data cannot have the same solution after some time t. Okay, this is the thing. So, this one is only, that is what I am telling you, that only in the nonlinear problem, I am knowing only the data at t equals t1, it is irreversible phenomena. So, only I have to move forward. So, now I am taking just a 3-point schemes. So, this one right hand side I am just representing by the solution in the grid. The solution is depend upon 3 points. Okay, u of in plus 1 is equal to h of vi minus 1 n vi vi plus 1 of n. Okay, this is the scheme I am giving, and it should be conservative form, means you should be equal, this should be able to rewrite in this fashion. Then I will say it is a conservative form. Conservative form. What it means? Integral has to be remain. Conservative form means total amount. For example, initial mass of the integration is u of x0 dx is equal to the mass has to be maintained. Like I told, the water and the oil. Amount will be the same for any time t. Position will get changed, that is all. Total amount should be the same. That is why it should be in this form only. Okay. The integration means summation of vin plus 1 into h, isn't it? Riemann sum. That is equal to here summation of vin minus infinity to infinity I ranging from here. This will get cancels. If it is conserved, this will get cancelled. Summation of, isn't it? Plus summation of I ranging from 1 to, sorry, minus infinity to infinity, f of I plus half, minus summation I ranging from minus infinity to infinity, f of I minus half. Both are same when is I is ranging from minus infinity to infinity. So this will get cancelled. So integral remains, it is conserved. So that's the conservativity is important here. Now here mathematicians will face a difficulty. Do the approximations, I used the Taylor series. Okay, but Taylor series valid, only function is differentiable. But my solution is not differentiable, not even a continuous. Naturally, for physicists, they don't care. For mathematicians, you have to prove the result, no, step by step. When your solution is not continuous, how can you use the Taylor series? Because you know that mathematical difficulty we arise it. How do you use the Taylor series when the solution is continuous? The beauty is that conservativity will help you correctly. If it is not conservative scheme, then you cannot use the Taylor series. Here, why it helps you? Even though solution is discontinuous, still I can use the Taylor series. Okay. So let us take a shock. So up to here some point it's a constant. Up to here this is a constant. Okay. There is a discontinuity. Taylor series is not valid at this point. Okay. But it conserves the area. That means up to here the solution is smooth, I am using the Taylor series. Up to here the solution is smooth, I am using the Taylor series is valid. But it has to preserve this condition. That means this area has to be, total area is same. To preserve the area, it has to jump. Okay, automatically. That portion you don't use the Taylor series, but Taylor series and conservativity jointly together, that is value. Here you don't care about the Taylor series, but the area has to be preserved. Preserve the area, automatically it will jump. At that time, even though Taylor series is not valid, but other parts of the Taylor series is valid and conservative. Total area remains the same. That is meaningful. Okay. So this is another part. Taylor series is valid as long as nonlinear problem is in the conservative form, and it's even though discontinuous solutions are valid for the Taylor series. Okay. So now start to develop a numerical schemes. So I told that when wave is moving from the left to the right, that means speed is positive, it goes to the backward scheme. Otherwise, when the speed is negative, I use the forward scheme, it used to jump to that one. Okay. So thus a schemes called upwind schemes. Upwind schemes, according to the direction of the wind, upwind schemes. Upwind schemes. Okay. Upwind schemes. So if f is increasing, suppose whatever may be the f is nonlinear, f is increasing, what it should take? F dash is positive, the speed is positive, it should take always backward. F is decreasing, f dash is negative, speed is negative, therefore it should automatically takes the forward. So such an attempt was how to develop such a schemes, automatically it should switch over. Okay. So good to know. How much of time I have, or can I take in the, how much of time I can take up to? 25 minutes is there. Okay, good. So good now. So now I am coming to there are three kinds of steps now. One is finite difference, finite volume, and the finite element method. Which one I should choose? Which one I should choose? Which one is the better for the conservation law? Okay. Of course, finite difference is the cheapest, less amount of computational work, time consumption. Finite element method takes the more time, because in the two dimensions, your domain is like this, you are dividing the rectangles, triangles, quadrilaterals, like that. Finite element method, like here. Okay, this not okay. Right here in two dimensions. Use the rectangular grids and so on. So the finite difference means these grid lines are parallel to the x and t axis. Finite difference means the grid lines are parallel to the x and t axis. Okay, and they are replacing the derivatives by the finite differences. Finite difference means my grid lines are parallel to the x and t axis, and the derivatives are replaced by the finite differences. That is what Vin plus 1 minus Vin by h, that is the derivatives are replaced by the finite differences. Here now that this is the finite difference method, but the difficulty is here that all the grid lines should be parallel. Suppose your domain is something like that, then you will miss a points in the domain when you make the grid lines are parallel. The finite element method takes care, because you can small meshes, you can go and curve like boundary, like here is a triangle, and you can map to a triangle region map, and you can study that. Okay, finite element method helps this make it clear to the fit into the domain, but it is an expensive. So, but here finite volume is something lies between finite element method and finite difference method. So, what I should do is that I have to preserve the area. See, I have to also wanted to preserve the area. That means total integration in the domain, in the for example, in the finite element method, I will compute the solution at the grid points, 4 values. Okay. Finite element method is that I want to conserve the answers in each step, because total area has to be conserved. So, instead of that one, I will take the average of a solution. I do not want to find the solution here, average of a solution. That is all I wanted. Sum of that maintains the total average, total solution. On each grid, I will find an average of a solution. I want to preserve the total area. That is why I know that initial data is area, and I would like to preserve it. So, in the finite element method, I am not interested to go to the every vertex find the solution. I wanted only the average of a solution. So, finite volume method means I will take the same grids as in the finite element methods, rectangles and triangles. I find the average of a solutions. So, it reduces the, for example, to find a solution here, I have to use 4 basis element, isn't it? This vertex 1 basis, this vertex 1 basis, this vertex 1 basis, and this vertex is another basis. If you want an average of a solution, only one basis is enough, that is a constant. In the finite element method, for all test functions, you replace a constant there, then it gives the finite volume method. Okay. So, it is something lies between not computationally expensive as finite element method, but more expensive compared to the finite difference, and since every triangle or rectangle, I want to preserve the original area of the solution to this computed solution area. I am maintaining every cell the area. So, in this way, I am more interested in the conservative property, means preserving the area under the on each triangle, rectangle. So, finite volume is the best for this one. So, on every cell I will find the average. So, solution is not continuous. This triangle, this solution is differs from this one. Therefore, discontinuous Galerkian method is the best. for the finite volume methods. Finite volume discontinuous Galerkin method are the best one. So now, keeping in that mind, now I am not interested to find the solution at the point I and xi and tn. I want to find an average of a solution. Okay, I want to adopt the finite volume method is the best. That is what Goodenough does it. In 1D, both are can be interpreted as a finite difference, because we are not dividing the domain into triangles or rectangles, only small intervals 1D. Okay, so he does that. How he starts? Ut plus f of ux is equal to 0. This is my conservation law. Okay, now look at here. Now, so I am interested to find the average of a solution. Let us take in a finite difference way. Let me start with a finite difference way. Okay. So if I know the average of a solution at a time t equals tn, average of a solution, I want to find the average of a solution in this interval. Okay, tn plus 1 also corresponding solution. I am not finding the value at the grids, average of a solution. Okay, in that's why he takes the following notations. Xi's are replaced by sequence. It discretizes the xi minus half, xi plus half, xi plus 3 by 2 instead of xi's. In the finite difference method, we take xi plus 1, xi plus 2, and xi minus 3 by 2. I am going to define the finite difference method, finite volume method. I want to find, I know the data here. For example, my initial data is Vi 0, in this Vi plus 1 0. So how to find Vi 0, Vi plus 1 0? Because you don't know, function may be discontinuous. So he defines that conservative way. Vi's zeros are given by 1 by h, xi minus half to xi plus half, okay, v of x0 dx. Average of a solution. Solution may be discontinuous, I don't care, but it will be integrable. Any bounded measurable function is Lebesgue integrable. Okay, this is meaningful even for a discontinuous function. I am not finding, for example, if I take the Vi 0 at the point xi tn, solution may be discontinuous at that point. You don't know whether to take the left value or the right value. But when I take the average value, okay, that fits well. So now I redefine this, the finite volume method. I discretize the initial data as like here, Vi minus 1 0. Now xi plus half, xi minus half, you understand that's one. You follow it very, I don't have the color pens I have here. Oh, yeah, I have red. Okay, now come to the stage. This is t equals tn plus 1. Okay, now start here xi plus half, xi minus half. Okay, here I know the data here Vi 0, I know the data here Vi plus 1 0 and Vi minus 1 0. I want to find a solution here, average of a solution on this line. I don't want at every point. In that interval, what is an average of a solution? Okay, that he tried to do it. So it is like left side is Vi minus 1, right side is Vi 0. There is one discontinuity at the point xi minus half, xi plus half Vi 0 left value, right value is Vi plus 1 0, and such a problem are called Riemann problems. Okay. It is the superpositions of many Riemann problems. So what is the Riemann problem means? Is if your initial data u of x0 is equal to ul if x is less than 0, ur if x is positive. Okay. So people try to find, is it possible to find an analytical solution, except if f is a convex case, you can find it, but if f is not a convex case, you cannot find a solution other than it's a linear functions. But Riemann was able to find a solution to this problem. Later mathematically proved that it's an entropy solutions. For this only one jump, ul is equal to ur, the solution become constant, solution is also constant because it is involved. If u is constant, ut plus f of ux, x is outside, is also 0. Okay. Therefore, it is a solution fine. When there is a one discontinuity is there, okay, how to find a solution? Suppose f is convex. F is convex. So, by knowing because I want to find an entropy solution. So, now suppose ul is greater than ur, ul is greater than ur, left value is greater than ur. Okay. In this case, how to write a solution? U of x, now there is only one jump, this side is ul, this side is ur. What is this line? This is nothing but x is equal to st, where s is equal to f of ul minus f of ur by ul minus ur. This is nothing but the Rankine-Huygens condition, x dash t into ul minus ur is equal to f of ul minus f of ur. I have to satisfy the weak formulation. Therefore, I will set this one ul is equal to ur. Okay. Now, and ul is greater than ur, the speed is f dash of ul, the characteristics will come and hits like here. So, the information comes and hits on the line x is equal to st. This discontinuity absorbs the information from here to this one because it does not allow this side. This information it sucks here and it won't allow us to this side. They don't hit each other. So, it moves and satisfying the Rankine-Huygens condition. In the case of f is convex, ul should be greater than ur. I have taken the data as itself. So, it satisfies an entropy condition. Suppose ul is less than ur, ul is less than ur, then even though data is discontinuous, solution cannot be discontinuous. If there is a discontinuity, ul should be greater than ur, then only it is a discontinuity is allowed. Otherwise, it is not an entropy condition. So, what he does was ul is less than ur, then the characteristic looks like here 0. This is x is equal to f dash of ur, because ul is less than ur, f is convex, f dash is an increasing function, therefore f dash of ur, f dash of ul is less than f dash of ul. This side the solution is ul, this side is the solution ur. You don't know how to fill it up the gap, okay, because it is by characteristic method this and this goes. But I have to, it should solution, I have to introduce a one solution, it should satisfy the conservation law, and discontinuity is not allowed. Continuous solution I have to do it. I have to fit the continuous solution here. That is given by, you can check that f dash of inverse x by t is the solution. When x is equal to, x is equal to t into f dash of ul, so f dash of ul, f cancels, then it is allowed the continuity is here and it gives the continuous solution here. ul is less than ur, if u is f is a convex, solution has to be continuous, okay, it allows that. It is a real entropy solutions. So, but it is complicated because when you do computation, every step solving a Riemann problem is very expensive. Okay. So, what it does was, I think I will go back. Okay, then I will explain later, okay, after the next class. So, tomorrow I will explain what is the Godunov scheme, how it is an upwind, and what are the other upwind schemes. Mathematically, is there exists a scheme which is not upwind, still it is a working. Okay, among that, which one is the best? and convergence analysis. I state some of the results and the proofs you can see in my notes. Okay. So, I am trying to supply the background of each theorem. Okay, then fine. Yeah. So, I think this, if you feel that if you want mathematical proofs, I will replace this physics part. I think this is better. We can always read the notes. Okay, then fine.
So any question from today's? So offline participants and as well as online also, you can ask the question. Online. Online, is there any questions you ask? Yeah, they can see because we are recording it YouTube, sir. Sir, here YouTube live is going on.
See them?
They can see. Oh, you want to see them? Why? Actually, sir, when actually two parallel we are doing, suppose it is YouTube live, and how the board is not there, then project by projector we can add them. Yeah, yeah. But for because of board actually we can't, we are not able to do that. Yes, yes. So anyhow, so sir is here. So tomorrow he has.
You are working in this area. No, you ask the basic questions to understand. Theorems and proofs you can always see if you have a technical difficulty.
Oh, Zoom meeting. Okay, so then thank you, sir, for today's lecture. So I think a hands-on practice or something that one. Yeah, yeah, that things also will do in the hands-on practice session.
I think I get the scheme, but I will do the scheme. Yeah, maybe I will explain at that time.
Okay.
Before start the computation.
Sir, then. You have question? What? YouTube link, yeah? Oh. YouTube live is going on, na? So they have some question.
Okay, okay. What is that?
I have question.
You read it.
Yeah, okay.
Because it's too small for me. It's, I have some YouTube, yeah, they can use it. Yeah, let them ask. You need this also.
Question is,
Ah.
I have questions are you put in matrix form of finite difference scheme to get solution using initial guess.
No, question is not clear for me.
You put in matrix.
In matrix.
In matrix form of a finite difference scheme to get solution using initial guess.
What it means? No, I am taking the real values. There is no matrix in the data. Yes, you can ask him. What is that? I have a question, sir. You put in matrix form of finite difference scheme to get a solution using initial guess. No, you have to develop a numerical method. But you know the initial data. From that, at t is equal to 0, you know the solution. I want to compute the solution at t equals t1. What is the numerical method? It takes, that's what I am going to explain.
Can go by Jacobi method.
No, it is not a matrix. See, This is not a matrix. I am not inverting a matrix. See, Jacobi method is meant for the Ax is equal to B. Oh, in that connection she is asking me. In the beginning, I told that how to see. The problem is that why I am going to there are two kinds of methods inverting Ax is equal to B. Okay. One is direct method like Gaussian elimination, LU decomposition, Cholesky decompositions, and so on. But I have a difficulty there because this computer what does was it doesn't take the exact value. For example, pi into come into picture. It takes 3.14 or something. It is not every operation it does an error. Suppose you have a billions of operations. Every operation there is an error. Your computed solution may be far away from the exact solution because of this round of errors. Okay. How to overcome this? So it is better to look a solution as a sequence. Xn plus 1 is equal to sum f of xn. As n goes to infinity, the sequence converges. If that sequence converges, if you prove mathematically, then there is no question of round of errors. Solution is continuously depending upon the initial data. Okay. So their iterative methods, we use that Jacobi method, another famous. What is another one? Iterative methods. Gauss elimination. Sorry, what is that? Gauss-Seidel method. See, I am getting it. Gauss-Seidel method. Okay. Likewise, that is why we are going to the iterative methods. Why is the necessity of studying the iterative methods? Because direct methods, problem of a orthogonal matrix, some matrices it works, but arbitrary matrices I may not be able to by using the direct methods, because this round of errors is another problem. To avoid that, I looking at solution as a sequence. Iterative method they looks as a xn plus 1 is equal to something, b of xn or f of xn, and the spectral radius is less than 1, it converges. Okay. For example, your matrix is a strictly diagonally dominant matrices, always it converges. So that is why that Jacobi method, that is why we are studying the iterative methods to solve Ax is equal to B. Direct methods we have problems. There is a famous Wilson matrix. It is a 4x4 matrix. Okay. You can see on your Google and go that what is the Wilson matrix. You make a small change in your data in the matrix. For example, your entry is 1. You put 1 plus 0.1. It can happen because you don't know exactly the data. You don't know the exactly value of a pi. You have to do the approximation in the data. When you do the small approximation in the data, it may create a big change in the solutions. That is why in mathematics, in the Hadamard sense, mathematics is well posed. A PD is well posed. Solution should exist. Solution should be unique. Solution is continuously depending upon the initial data. That means if you make a small change in the solution data, there should be a small change in the solution. Same numerically it should be valid. Okay. A small change in the data Ax is equal to B. B, if they make a small change in B or A, there should be a small change in this such a thing. So for example, the Wilson matrix, he shows a small change in the data, it gives a big change in the solution. So they are not direct methods, sometimes have a problems. That is why we go to the next step, iterative methods. They are essential. This is a part of the numerical analysis. So there it's a matrix comes, we go to the Jacobi, Gauss-Seidel, relaxation methods. See, the words are not, suddenly it won't come. Okay. Maybe in that sense,
Yes. Okay. So this conversation and question and answer also will take. So sir has because the sir is also there in the means tomorrow. So we'll continue it. Thank you, sir. Okay, sir. Thank you.
Anybody is working on numerical methods, conservation laws, or what exactly? What exactly you are doing on conservation? Huh? Zero skip higher order. that you can go to the header. First, I will do a problem. First, I want one stream is converted. Don't care about the filling short of one section. How much big algorithm it is. You want one stream. First, you develop that. After that, you try to do the analysis.
Audio also will come.
Both will be in our order.
No, they knows actually. When you call
So, in my lecture, only I have
this
developed
audio
the
also will
order.
come there. Online speaker.
So once you know that, after that you can go to the, we know all.
Okay, thank you, sir. Okay, so now we have another session. This is online session actually. Okay, thank you. Okay, no. Now we have an online session, online talk by Professor S. Dharmaraja and Professor and former head, Department of Mathematics, IIT Delhi. Sir already joined with us. So, sir, can you hear me? Just 1 minute, sir. Just audio you can. Yeah. Hello, sir. Sir, voice is not coming. 1 minute, sir. Just a minute. Actually, some audio issues. Okay, so some audio things. Okay, fine. So before that, before going to start start this session, let me introduce. Actually, nothing to say because he is a big professor in this. It is my great pleasure to introduce him. So he has been with the Department of Mathematics, IIT Delhi since 2003. So where he is currently a professor and joined the faculty of Bharati School of Telecommunication, Technology and Management from 2013. So he is a professor in the higher administrative grade from 2020. He appointed as institute chair professor. Okay, so some audio things. Okay, fine. So before that, before going to start start this session, let me introduce. Actually, nothing to say because. Okay, so he appointed as institute chair professor from July 2019 to June 2024. So during this period, he served as a head Department of Mathematics. He appointed as Jaswinder and Tarvinder Chadda, chair professor for teaching and research in the area of operation research from 2010 to 2015. He has visited in different countries like USA and that institutes, New York University, Duke University, Emory University, University of these are in USA, and University of Calgary, Canada, University of Los Angeles, Columbia, National University of Columbia, and University of Verona, Italy, Shanghai Kunkan University, Korea. So University degli Studi the Salemo, Italy, and University of New South Wales, Australia. And in short, this is actually in short I am doing this introduction. Anyhow, so his research interests include applied probability, queuing theory, stochastics modeling, and performance analysis of computer and communication system and financial mathematics. He has published over 110 papers in referred international journals and over 50 papers in referred international conference in this area. He is an associate editor of International Journal of Communication System and managing editor of OPSET. And also he has a lots of book already has published. Okay, so in this short, actually, it is at least things I introduced. So anyhow, I am going to hand over to sir. Sir, please continue.
Is visible, sir?
Papers in referred international
Yes, sir. It is visible.
over 50
Thank you. Thank you.
papers.
Internal
Managing
Valley
editor of
district.
OPSET.
And had all the graduation in Chennai,
Also, he has a lots of
Presidency College,
book
Anna University, IIT Madras,
already has
then
published.
postdoc,
Okay, so
and
in this short, actually,
Duke,
it
then
is
again another
at least
postdoc.
things.
Department. So I'm thanks to them to provide such a facility for me to give a invited talk sitting in the good network connection. Had all the, so I'm happy to be here in the giving a talk in SRM, and I'll be traveling to SRM sometime in next month end. So I will meet in person some of the people there when I visit SRM. Let me give the talk here. And another one is I want to thank Professor Ritesh to invited me to give a talk here. So if Ritesh is there, then I'm just telling thanks to him. Yeah. So my talk is basically machine learning approaches for variable annuity pricing under regime switching market dynamics. So this is purely a financial mathematics research problem, in which we have solved using a machine learning techniques. So I thought I can encourage the young researchers as well as faculty members how to apply the machine learning technique to involving in the pricing for any derivative pricing and so on. Before that, I will tell you what is the meaning of a variable annuity. It is one particular service which is provided for the insurance. Nowadays, we have many insurance policies, and every time you will see the different plan. Whatever the plan which we had it like 30 years back, but every 5 years or every 1 or 2 years, the plans are keep changing. And those days, whatever the money we invest in the insurance, that money is as a fixed deposit types, and you never know how the money is used by the government or the insurance providers, for example, LIC or whatever the different service providers. But over the period, people thought, why not we can use this money in the market to get some more better than the fixed price, fixed interest. So what are all the ways we can invest the same money which we deposited, which we give as a premium to the service provider, to the insurance provider, and they use that money to invest in some stock and so on. And that way, they also get a lot of money out of it. So now, as a customer's point of view, what is the good plan in which we can have a more benefit than the typical benefit of after death you get a lump of money. and during your some of the period you will have a monthly some sort of a pension, some amount. So other than this, what are all the different ways one can pay to the customers who are be the people to give the premium money? So this variable annuity is the you give the annuity in a different form. So that the variable word means there is a different plan. So now, as such in India, we don't have that all the service policies or all the plans as such we don't have. But some of the European countries and the American countries as well as Japan, this type of different types of plans are possible in the insurance. And in India, we have a very limited, but still our research is completely on global, starting from US as well as Europe and eastern side of Japan. So what we have done is we have found out how the mathematical model can be developed and how one can do the pricing. And when you do the pricing, how much the empirical data can be used to have a good estimation. So for that, we use the machine learning approach. And this regime switching is some sort of a cluster in which we go for the different plan according. So this is a brief idea about this whole talk. And this is too technical for the people who does not have a complete knowledge with the financial mathematics or using a stochastic process. So one can download the same paper which is in my homepage. If you go to my homepage, I have given the link also. So from there you can identify the download the paper, and you can read the complete paper in detail. So this talk is based on one of my PhD student. His name is Sarfraz, who recently completed PhD. And now he is a postdoc in Ashoka University, Delhi. And so I'm presenting his work in this talk. And the slide is prepared by him. So, yes. So this is the outline of the talk. So I'm going to give a brief introduction about this talk. Anyway, I have given, but still some more technical things I'll explain. And then what is variable annuity, what are all the different guarantees, then what's the modeling approach we have used, and how we did use the machine learning and using the empirical data, and how we got the results. So that's the way the talk goes. Yes. So the motivation I have already given. Motivation is many of the insurance plans, which is very old, but now over the period of time, we want to maximize whatever the money which we invest into the insurance. So that is as a customer's point of view. Whereas the service providers, LIC or ICICI Lombard or any other insurance policy providers, they need how to maximize their returns by investing the money and so on. Therefore, the variable annuity play a very important role. It is called a market-linked investment growth with insurance guarantees. So if you see the word guarantees investment and everywhere, there is a randomness in it. There are so many dynamics keep happening, and whatever the dynamics are happening, how we can maximize the money what we have, the wealth of insurance company, as well as how we can make the customers happy by providing a better service. As far as our research is concerned, we go for with the stochastic behavior. So some of the things, interest rate, many things are stochastic, and there is a volatility involved, and there is a market is keep fluctuating, and there is a many cycles are keep changing over the short cycle and long cycle. So these are all the things makes the stochastic model become very difficult. So what we attack is we understand the existing literature, and then we use our own ideas of stochastic process, whatever the knowledge which we have gained over the time, and we made it and made a better model then getting the results, then comparing with the existing result validation. That's the way we conclude the paper. So the research gap. So basically, we have used all the literature, and we have used the actual Nifty index also, and we have used the nice regime switching model, and we applied the machine learning techniques to get the results. So this variable annuity is the very important word. It's a tax referred retirement products that allows the investment in sub accounts which embedded guarantees against the downside risk. Actually, this comes under the risk analysis. So when you invest the money, how much risk you will have it? And the question is how to reduce the risk. We cannot avoid the risk. We can reduce the risk. So whenever the risk is going to come, how to reduce the risk by making a proper strategy. And we make a stochastic model for that and getting the results. Yeah, these are all the different common guarantees available. By seeing the word, you can make out it's a guaranteed minimum death benefit. It's a very simplest one. And the minimum accumulated benefit. So over the period, you will have some pension types and the guaranteed minimum withdrawal benefit. There are some insurance policies, you can withdraw some monies also, because sometimes we badly need some money, and we can withdraw some of the money also. So there is a withdrawal benefit. And next is a guaranteed minimum income benefit. So not only the sort of pension, there is some sort of income also can come. So therefore, there are different plans in which we can sign up the insurance. Accordingly, we can have a benefit. Actually, all these guarantees are with the function of age of the insurance. Suppose somebody is having an age less than 40, you may have a different plan which suits to you. Suppose the somebody is between 40 to 50, then some of the plans it may not be good for due to the health condition and things like that, based on financial condition also. If it is above 60 or above 70, then due to the health condition, even the insurance also, they have a different plans. Some of the plans may not work for after some age. So therefore, age and wealthy of insurance person also important to sign up for the different guarantees. Yes. So this is the payoff function. So always we want to maximize whatever the money we are investing at the end of the maturity date. We want to maximize that. So that is going to be the payoff function. Yeah, this is a very important concept which we have introduced called the regime switching rationalize. So what we do is whenever the stock market or the dynamics goes below some threshold, then we go for converting the whole thing into two regimes. So above the threshold is the one regime and below the threshold is the another regime. So whenever it is in the different regime, then you consider the different strategy to forecast or to predict or to the pricing. The next question comes, how do you fix the threshold? So that is also you need a good statistical data analysis to tune that threshold point. So sometimes you keep the threshold point at the 55%, or sometimes you keep a 45%. So you can tune the threshold point also based on the background empirical data. And in here, we have used the regime switching as well as we have used the hidden Markov model. Hidden Markov model is nothing but you get the empirical data, then you fit the nice Markov model and feed all the parameter values. Then based on the Markov model, you go for the prediction. So from the past history, you feed the parameter values. You feed the parameter values for the Markov model. And after your model is done, then you go for predicting what will be the future. So those who are very comfortable with the probability and the stochastic process, you can easily able to understand what's the meaning of transition probability matrix from one state to another state. whenever you have a regime. For example, if you make a regime is a bullish or bearish, this is a region in which you divide. Then how the transition happens, and once you know the transition probability, what is the stationary distribution? That means what is the time invariant distribution is going to come? What's the proportion of the time the system is going to be in the state bullish or the bearish? Let me see the time also. 12:10. Okay, so I'll try to complete before 12. I'll take another 10, 15 minutes. Yes, so this is a very important equation. This is called the stochastic differential equation. So the increment over the S of t, that is a function of dt plus a function of dwt. So whenever you have a increment over the wt, this is a Brownian motion, then this equation is called the stochastic differential equation. Usually we won't write the differential equation usual form of d by dt form, whereas we write increment of function of t is r times a function of t, s of t with the dt plus some volatility, s of t plus d. So this is the way we write the equation, and there are many ways of finding the solution for a stochastic differential equation. There's a closed form solution, there is a numerical solution. If not, you can go for the Monte Carlo simulation. If some of these functions are very nice, very simplest form of a stochastic differential equation, you can have a closed form solution itself. But if you have a volatility is going to be a function of t and s of t, then it is very difficult to get the closed form solution, and one can go for the numerical solution. And here we have used the numerical solution, and then we use the nice statistical data analysis to estimate the parameters using a machine learning. Then we predict the pricing. Yeah, again, we have a stochastic differential equation for with the volatility, stochastic volatility, because once you have this function is a function of t or a stochastic process, then we call it as a stochastic volatility form. If this is a constant, then it is easy to get the closed form solution. Yeah, now we are coming into why machine learning. So whatever the stochastic differential equation we have, so those cannot be solved in a closed form. So you need either numerical solution or Monte Carlo simulation. And once you go for it, then you need how to estimate the parameters which involved. So this machine learning approach is a very good approach to use the data analysis part nicely. And these are all the benefits. It has more speed, scalability, and uncertainty quantification also possible in a nice way. Yeah, so we use the Gaussian processor regression for predicting. So you would have come across the easiest linear regression model, but we have used the Gaussian processor regression model for estimating the parameters. Yeah, this is one of the machine learning techniques. It's a neural networks techniques. So this my students understood, and I'm not expert in neural networks. I'm expert in stochastic process. But my student was telling, for this problem, one should apply the machine learning, in particular neural networks. With that combination, we can able to do the prediction faster. Yeah, here hidden Markov model I said. And for the, I said, we use the actual data. So that time series data is taken from Nifty 50 and the S&P 500. And our institute has the subscription over collecting the data every month, day one. Every date, January 1st, February 1st, March 1st, like that. And the first day we can get the past data, every month data in the central library. So the students go there and download the data, the time series data, then they use the analysis. So it's a real data is used. Yes. Yeah, that's what I was telling. The data sources from both US and India. Whereas my other students, they have used the Japan also. So, and in another paper, we have used the European data set also. Yes. So how the descriptive statistics gives the result, what is the mean for the different range of years, and what is the standard deviation, skewness and kurtosis. Basically, mean, skewness and kurtosis will give a complete idea about what's the distribution it happens. So you can always compare with the standard normal distribution. You can feel it, how much it is deviated from the normal distribution. Yeah, this is the pricing result. So we are able to do the pricing for the different years. It's a maturity. Capital T means maturity year. Either 5 years, what will happen, 10 years, what will happen, 15 years, what will happen. That you can feel it. Always, more you go for predicting for a longer duration, the percentage will increase. So that you can feel it. That's a comparison. Yes, that's correct. Yes, so how much the models are accurate and how much computational efficiency, because we have used the neural networks and we have used the hidden Markov model in a correct way. Therefore, we are able to get the things faster and it is less error. Yes, so this comes under risk management. So the way we have done the risk analysis, there are many ways we can do that. For this problem, we have used the regime switching and the hidden Markov model and the machine learning techniques. With this combination, we have done the pricing. But this is not the only way. Based on your problem statement and based on what is the output you want, and based on what is the input which you supply, accordingly you can go for the different mathematical strategy or mathematical methods to analyze it. Yeah, that's what I was about to tell you. It's an integrated regime switching, local volatility with the ML methods. We have integrated both because there are many research articles with the regime switching. There are many articles with the stochastic volatility. There are many articles with machine learning. Machine learning is a method, so you can apply wherever it shoots. So here we have used it for pricing for the variable annuity. And for the data, we have used both US and Indian markets. Whatever the data is available with you, you can always use the correct method. And first empirical study for the variable annuity pricing under COVID-19 for India. So we have applied for the COVID-19 that period data set as an empirical data set, and we have find out the pricing. Yes, if you have any questions, I can answer, please. Yeah, if you have any questions, I can answer. Yeah, 12, 17.
Am I audible to you?
Any questions? Yeah, please.
Thank you, Professor Dhamraja. This is Ritesh.
Yeah.
Thanks for joining with us.
Thank you.
So, one of the participants is having question.
Please.
You can come here and ask. Sir, you can stop presenting your screen. Professor Dhamraja.
Yes, I have done it.
Sir, it's what you solve. This is a risk management program. So that VAR concept are not using here, and where you are collecting all the data that I can't understand. And what is the model? Means how can we use that machine learning technique? All these things I did not understand. Can you please explain?
Yes. So your question is a valid question. The number of slides which I have prepared, in that I have skipped how the machine learning, how the data is collected and how the data is used in the neural networks to apply the estimating the parameter values. So those things are I have not included in the slides because it is going to be more detailed discussion about line by line. Therefore, I have given the talk how I moved from the given data set, apply the machine learning or the neural networks, estimating the parameters and the stochastic SD we have, and having the prediction results and feed the values. So all these steps are explained in my research paper with the same title. If you go to my homepage and if you download that PDF file, which is available with the name Sarfraz and myself, and the detailed line by line I explained.
Thank you, Professor Dhamraja, for answering
Yeah.
that question. One more student want to ask a question.
Please. I want to motivate the students to listen to the talk and they should get the feel how it is possible. So I don't
There is
want
a
to
motivation
explain
among
everything
the
in the
students.
talk.
Yeah, I can see questions are coming.
Please. Yeah.
My field is string theory and working using the Monte Carlo solution used for numerical event. You
No,
can
he's
hear,
in Delhi.
oh, yeah. So you can able to hear me?
Yes. I am now. Last word till Monte Carlo. I was listening. Can you go ahead?
Yes, I am in our working. I'm using that numerical solution. It is possible to give me some suggestion books, basic according to that Monte Carlo solution.
So you want to know the textbook to work on the Monte Carlo simulation of queuing models.
Yes, I need that one.
Okay.
Suggestion.
So, yeah. So just write a mail to me. I will just cut and paste some of the books in the website and I will give you the link.
And I also working.
What is your name?
Harshini, sir, Harshini.
Ashwini. Okay, I'll remember the name. You write a mail to me. I will just cut and paste and I will give you by email.
Okay, so I'm also working in transition state analysis also.
Mhm.
And also for defining how the risk management in our work we are considering how the risk management and using the Gamblerian problem we are working in gene theory. And we are easy to it is tough to find that the risk management how the gambler is working in queuing prosperous. So and we so we have now only go through that.
Please. I'll be coming to SRM campus on February 26th afternoon.
Okay.
And you please coordinate with the Indumadi ma'am. She is a mathematics department faculty.
Okay.
So you contact Indumadi ma'am, Max faculty, and so I'll be there in February 26th afternoon for 3 hours there.
Thank you so much, sir. Thank you.
Yeah. You want to ask the question? Okay. Thank you, Professor Dhamraja. I'm not an expert of this area, but I understood that you are trying to switch between the bearish and bullish
Bullish.
market, and you spoke about the threshold, setting the threshold. So is it all heuristic, or there is some algorithm also to find out that cutoff or
There is
threshold?
algorithm. There is algorithm. They also use a machine learning technique to estimate those threshold parameters. So everywhere now the AI and the ML occupy. So anything which has the past history, they do the better job using a machine learning than the earlier heuristic approach or standard approaches. So many things are now dynamically they do the things with the machine learning or AI techniques than the usual standard ways of finding the values.
Okay. Thank you for this. Any other question? No question. then let's thank the speaker, Professor Dharmraja, for joining with us and giving a nice talk.
Yes.
It was quite motivating, even
Yeah.
for me, though I'm not an expert in this area, but I understood uh, whether we are having PhD degree in physics, chemistry, or mathematics. Most of the time, we are financially illiterate. So, thanks for enhancing our understanding. Thank you very much.
Yeah.
Hope to
So
see you.
I am a person. I always feel like when he invited talk, the audience are in the very heterogeneous. So we should make them understanding the basic things.
Yeah.
And those who are very much interested, they can always go and read the full paper. So that is my way of giving a talk. So I'm happy to be in the online talk, and thanks to Sri Mahatava Vaishnava Devi University, Jammu, to providing such a facility to give a talk in the online to all of you. And I missed the in person also.
Yeah.
So I'm sorry I could not able to come in person.
No problem. So
Thank you.
convey our thanks also to those people.
Yeah, thank you.
Thank you. Thank you very much.
Thank you. Yeah, bye.
Let's give a big round of applause. Is there any recording going on? Hello. Hello. Audible? It's not working. Hello. Hello. Hmm? Hello. Fine. Shall I start? Shall I? Huh? Are formal introduction, such a big person is standing. No, no. They know me. You know me? No. So actually, as per the schedule, I am supposed to talk about the neural ordinary differential equation. But yesterday I said that I will do Lex Frederick and Lex Van scheme, because that is what Ratan has taught you. And I wrote the fluxes little bit incorrectly, so let me correct them first. Okay. So the today Professor Gowda also spoke about the numerical schemes, Godno method or something. So the idea is that I will solve these two equations. One is the linear equation ut plus ux equal to 0 with some initial condition, and I will solve the implicit Berger equation also. And some other initial condition. And the scheme which I am going to use is first order Lex Frederick. So Lex Frederick scheme and Lex Van scheme. Okay. So we will solve or compute the solution of these two equations in a classical finite difference finite volume approach, and then I will just show you how we can use the neural network also to do the same thing. So basically idea is learning the viscosity, learning. My handwriting is not good. Learning the numerical viscosity. So let us recall that the conservative approximation, if you do forward in time discretization, then the conservative finite difference scheme can be written as difference of these two fluxes, where this is your numerical flux, and there are certain property like it should be consistent, and it should have like satisfy or this approximate a derivative with some certain order of accuracy, the derivative of which is there, f of u x. So yesterday I wrote if I go for the Lex Frederick scheme, how this flux will look. So if we go for the Lex Frederick scheme, so if I write the Lex Frederick, in fact any 3-point scheme, because Lex Frederick and Lex Pendrop both are 3-point scheme. This is first order accurate and this is third order or second order accurate. So any 3-point scheme, if you are considering, there are many, then their numerical flux function can be uniquely represented as fi plus half is equal to 1 by 2 ui, or I can write here f of I plus fi plus 1 minus 1 by 2. I can write here something, a function parameter of lambda h lambda times di plus half and ui plus 1 minus ui, where fi is nothing but the flux computed at I, flux at ui. Clear? So if you use, so this h lambda is, so and lambda is nothing but the ratio of time step and space step. Professor Gowda discretized the domain and is shown. Okay. So now depending on the choice of this h lambda and di plus half, it is called the numerical diffusion, coefficient of numerical diffusion. So if I want to understand this, so for Lex-Frederick scheme, your h lambda is equal to 1 by lambda and di plus half is equal to 1 all the time for f of u is equal to u or u square by 2 in both the cases. For the transport case also and for the Burger case also, this will be always 1. So technically your Lex-Frederick scheme flux is 1 by 2 fi plus 1 minus 1 over 2 lambda ui plus 1 minus ui, both for Lex-Frederick, both for the linear as well as for the Burger equation. If you are dealing with the linear case, then your fi is nothing but ui, but when you are dealing with the Burger equation, your fi is nothing but ui square by 2. Okay. When you go for the Lex-Van der Rohe scheme, then your h lambda is nothing but lambda and your di plus half is your ai plus half square, where ai plus half is the wave speed or rho wave speed, which is defined as f of I minus f of I plus 1 minus f I divided by ui plus 1 minus ui, if ui plus 1 minus ui is not equal to 0, else it is f dash ui. Okay. Clear? So it's very easy to implement. It's the like first class of scheme when you go for the numerical solution of hyperbolic conservation laws. Any book will talk about these schemes. Very easy to code also. Okay. My idea was di plus half. How to learn this di plus half? It is a numerical viscosity. And actually it is also a toy problem. Okay, it's a toy problem. But when I was doing it first time, trying to do it, it took a lot of time because I wanted to use neural network and a lot of things were not known to me. So is this clear? We want to understand how we can learn di plus 1 half numerical viscosity, both for Lex-Frederick and Lex-Van der Rohe. Now we know that for the Lex-Frederick scheme, this di plus half is always 1. It's a constant function. There is nothing to learn. But when you want to use neural network, it's a good example, like whether your network is giving good result or not. And here you are having ai plus half. If you see, it is actually a d in this case. Okay, I'll write here. In both the cases, you can consider your viscosity coefficient d is a function from R2 to R, because d I plus half is taking two arguments, ui and ui plus 1, ui plus 1 and ui, and then it is giving you one fixed value in R. Is that clear? So you are giving two argument a and b, and it is computing and giving you some real valued number. So it's a mapping from R2 to R. So if we want to learn it, what kind of problem it will be? It is supervised or unsupervised, or it is classification or regression? Yes, it's a regression problem. If you don't understand this, then it's a regrettable problem. So it's a regression problem because we are trying to predict some number, some value, real value. If we are trying to predict some special states, finite countable set or as output, then it's a classification problem. So it's a regression problem. So we can do this by neural network, a regressor. Like if you train a regressor, you can do it. In the machine learning, if you go and fit the data using scikit-learn, linear regression, those things you can do, it will work. But since we are focusing on the deep learning, so I will just use one small neural network to learn this. Okay. So first thing we will see how we can solve them. So basically I'm going to compare the numerical result obtained by the finite difference scheme when you are using the exact viscosity of the Lex-Fatigue scheme and exact viscosity of the Lex-Van Roth scheme. You will get the result which is coming from the Lex-Van Roth and Lex-Fatigue scheme. But if I learn this by the neural network, how the result will come? Can we do that? Very simple problem, but why I'm discussing is because it contains all the steps. So basically skeleton of the program is same for any regression problem. Your data can change, but the flow, the entire pipeline will remain the same. Clear? So can I raise this? Okay, so what we are learning this diffusion coefficient. So first thing is that diffusion coefficient is important. Why we are I'll tell why we are trying to learn is another question, because I'm doing in a workshop, so we can learn. For this kind of problems, there is no need, for such simple problems, there is no need to use a neural network. But if you go to the modified equation approach and try to, or if you do the modified equation analysis of the first order scheme, so though you are developing the scheme for this type of problem, so if you take your Lex-Fatigue scheme, then if you go by the modified equation approach, you will be able to see that actually your Lex-Fatigue scheme approximate this kind of convection diffusion equation. So this is your term, I will write here beta. So this is your convection term, this is your diffusion term. So diffusion basically dampens the amplitude of the solution. So this problem does not have any viscosity involved. But if you go with the scheme where the viscosity is not there, you will be having oscillations, because this accepts discontinuity. So the idea is that you, instead of, so when you are saying that your numerical scheme is good, you are actually saying that our numerical scheme is approximating this for beta goes to 0 in the limiting sense. So that is called a vanishing viscosity solution. Okay, so that's why your numerical scheme should be able to mimic this property. Okay, to avoid unphysical oscillations in this solution. And basically, if you go for the discontinuous solution, they are non-unique, as Professor Gowda said, and we go for the weak formulation. And when we go for the weak formulation, you have infinitely many solutions. In the scalar case, it can be shown that that physically acceptable weak solution is the one which satisfies, or which is the vanishing viscosity solution. So that's why in any numerical scheme, this is your convection term. If you discretize it, there should be a numerical viscosity inherently present in the method, and depending on the viscosity, amount of the viscosity, it can be more, it can be low, your scheme will behave differently. So Lex-Federic scheme, as I said, your viscosity is lambda. Viscosity is what? D. D is 1 by lambda. Basically, that means delta x by delta t. That means it is bigger than 1. But in case of Lex-Federic scheme, your viscosity is lambda, which is less than 1. So it is having more viscosity. That means the problem is more diffusion. It is having, like, this scheme will represent the modified equation which has more diffusion. So the solution will dampen faster compared to this. And here it is less diffusion, so numerical oscillation will come. So you go and read the paper by Warming and Hayek on the modified equation approach in 1974 or something in JCP. Otherwise, R.J. Livek book is also there that talks about these things. But your question has, made me forget where I was. So we are trying to solve the regression problem. So yesterday I discussed, whenever you go for the machine learning, a deep learning approach, and try to develop or train a neural network, what is the first thing you need? You need the data. Okay, it's a supervised learning setting, so we need the data. Now the question I would like to ask, which scheme you want, which diffusion you want to learn first? Suppose if you want to learn the diffusion of Lex-Federic scheme, which is actually 1 all the time, so you have to generate the data using Lex-Federic diffusion, which is 1. So idea is that you generate ui plus 1 and ui as a random number, and it is always good to generate your input data which is scaled. So I am putting from -1 to 1. So any MATLAB or Python will give you the flexibility to generate such random number. So idea is that you generate, because our this is R2, it is going from R2, so I am generating 2 numbers. Okay, instead of ui plus 1 on ui, you can write here a, b. Let a and b are 2 numbers which are random number in the interval -1 to 1. So I will say, for the Lex-Federic scheme, it doesn't matter what your ai and bi are as your input vector, your target is always 1. Okay, always it is going to give you 1. So you generate lot of data. You take the random generator and generate a very large data set, and then your input data and corresponding label which is having the viscosity of that particular scheme will be available. In case of Lex-Federic, instead of 1, you will be having ai plus half, which you will generate using the row formula. So once you are having your data set x, which is nothing but the ordered pair u and v, UI plus 1 or UI, and your output target is having AI plus 1 half, which is 1 for the lax fatigue scheme and which is non 1 for the lax fan drop scheme. So data set is there. Now you can talk about the data set. So you generated the data set. After that, you have to think about the neural network. So you are going to push this input one by one into the neural network, and each time you will get something out as output. So how many input node should be there in such kind of neural network? If you remember, yesterday I was talking about input layer is having that data. I'm not talking about the data split. Data split, understand? Okay, that is also a thing. So once you generate the data, you have to split the data into 3 sets. One is for the train set, another one is for the validation, and third one is the test set. That is good point you raised. But I am talking about the architecture of the neural network. So since it is going from R2 to R, so our input layer should have 2 neurons. If it is from RD to R, then you will have D neuron. You are passing UI plus 1 and UI or URV or ARB. It's a tuple R2, vector in R2. So this is your input layer. And in input, in between, whatever you want to do, but in the output you have only 1 neuron in this layer. And then in between you can have many different layers and non-linearity. And after this output you can talk about the loss, which is pi theta, and then you do the backward propagation, keep on updating the parameter theta, your neural network will learn. Okay, so you have to first you have to generate the data, you split the data, then you have to define the architecture of the neural network. But this is a very small toy problem, so it is very easy, in fact, for all. At least this and this we know all the time. If your supervised learning setting is there, you always know the dimension of the input layer, width of the input layer, and width of the output layer. Always. In between you can do whatever you want to do. That is called your fixing the hyperparameter, number of layers, width of the each layer, what types of nonlinearity you want, what is the learning rate. That tuning you can do by grid search method, means hit and try. So once you are done this, so you have to train the neural network. Once the neural network is trained, you can use neural network in your scheme. Okay, so basically that is called inference. So let us walk through the code. So I'm walking. So it's a fresh code or freshly modified code. So this notebook I will share with you. You can read this notebook. So whatever I just spoke, it's here. So your in general 3-point scheme, the flux can be written in this form, where for the lax fatigue scheme epsilon I plus half, which is our D, is always 1, and the h lambda function is always 1 by lambda. Screen sharing. Visible? It's visible? Everything set or not? Visible or not? My mic is on here. This mic or this mic? This mic is on only. Hello. But you asked me that this is the microphone, no? But it is only for the speaker. So then you remove it, and again we have to choose this. Hello. Uh, watch out. So this is the commentary in one cell. I cannot scroll it. Why it is frozen? Ah. So now I have written this using PyTorch, because that is the only API which I know. TensorFlow also I tried to learn some time back, but PyTorch is much better for doing research. Okay, so you can use it if you want to do like MXNet. You can use that also, but this code is in PyTorch. So you have to import the PyTorch module, like import torch, and then you have to import its engine and which has all the functionalities modules. Then you have data, how you manage the data in PyTorch. So one module is there, so that is in the torch utils data. So from there we are importing tensor dataset and data loader, and then we are talking about the numerical solution of these equations. So basically always it will be arrays, vectors. So for handling with them we are importing NumPy library here module. Then for plotting, matplotlib, and after generating the data we want to split into 3 parts. So for that we are using the module from sklearn, model selection module, train test split. Okay, and since every time we want that reproducibility should be there, so we will be generating the we will be setting the seeds. Okay, so torch seed we are fixing to 42, and NumPy random seed is also we are fixing to 42. So basically random seed defines when you are sampling the random data, the seed will define where each time you will get, in what vicinity you are going to sample the data. And it is a small problem, so you can go and run it in the CPU also. But if you want to use GPU, then you have to go and connect change the runtime, and you can choose GPU also. By default, Colab will give you CPU. Okay, but I'm okay with CPU. So let me run this cell, and it is showing you the device as CPU. So it's running, and then you get the device. Network is slow. Anyway, by the time it is running, let us go and look into the next cell. So our device, it's showing its CPU, which we know. Then I wanted to choose the scheme for which I want to learn the diffusion. So I have defined a list. So first entry of the list is Lex Frederick, and second entry is Lex Van Droff. So the indexing in Python starts from 0. So if I put 0 here, so I am talking about the Lex Frederick scheme. That means the scheme choice will have Lex Frederick. If I am putting here 1, it will be Lex Van Droff. Then equation type, which equation you want to solve. So we are considering both the equation, linear as well as the Berger equation. Then I am defining one dictionary which contains the name of the scheme and the type of equation. and then I'm writing it here. So now your notebook is configured to learn Lex Van Drop on Burgers equation, because here I have chosen 1. If I put here as 0, and if you run, then it will show that Lex Frederick scheme on the Burger equation. Clear? So here we have set the parameter through which we are going to generate the data. And flux we know, if you, so I am defining one method called flux, which gives me the flux of the underlying scheme. So if my scheme is linear, my flux is u. If my scheme is Berger, my flux is u square by 2. Okay, because this I am going to use in my numerical scheme also. And then I discuss about the row speed. So this is the function which is defining the speed. So if your scheme is linear, or if your underlying equation is linear, then your speed is always 1. That's what we are getting. So for all the grid, you have all the time 1. So I am giving you and returning np dot ones, all one vector of what size? The size of u dot shape 0, means first the length of the u, and I am getting 2 vectorize. Yes. So basically the code which I have written here is calculating not only right flux fi plus half, it is going to calculate fi minus half also. So fi plus half and fi minus half. So for this I am getting one viscosity 1, and for this I am getting viscosity 1 in Lex Frederick case. So that's why I am having the speed. Also I use the word viscosity, basically speed. So speed is of total length of the vector u times 2. So it's n cross 2. So first column is for the I plus half, here it will be u. Second column is for the fi minus half. And if it is if you are having Burgers equation, then you are defining your speed using this Rankine unit average. So in Burgers case, if I solve this ai plus half, it is equal to fi plus 1 minus fi divided by ui plus 1 minus ui. But what is my fi? In Burgers case, it is ui plus 1 square by 2 minus ui square by 2 divided by ui plus 1 minus ui, which will be solved to ui plus 1 plus ui. You can cancel it out. So that's what we are doing here. Okay, if your denominator is bigger than this, if it is not equal to 0, then you are doing this. Otherwise, you are getting f dash u, which is u. So this is your value 1 and this is your value 2. So value 1 is for the I plus half flux, and value 2 is for the I minus half flux. And then you are returning the viscosity. But here, sorry, this speed. So here the speed is exact numerical scheme, for the exact numerical scheme. And then you can talk about the scheme viscosity. What will be the viscosity? So that you are calculating. So if your scheme is Lex Van Drop, you are calling the speed function here, and then whatever is coming from that, you are defining your viscosity. So if you remember, for the Lex Van Drop scheme, your diffusion d is a square, ai plus half whole square. So you are doing the square of the scheme, and in case of Lex Frederick scheme, your viscosity is always 1. Okay, so these things I am defining here. What is your speed? What is your flux? What is your scheme's viscosity? And then I am generating the data here. So for generating the data, I am simply using the np dot random dot uniform. So from the uniform distribution from -1 to 1, we are generating how many points we have to generate? 3 points, 3 cross n or n cross 3. So many points, each 3 point. You need 2 viscosity, so you need ui plus 1, ui minus 1. So 3. These 3 input give you flux difference at 1 point, and you have to do it for many times, like for lot of time in order to generate the data. So I am saying that the total data size is n. So I am here number of sample I am defining here. So it is generating the random numbers of n cross 3 or 3 cross n size, and then I have to generate the target also y. So y is nothing but the scheme viscosity, so which is passing that generated random data along with my args. My args is the dictionary which contains all the information, which scheme you want to use, what method you what equation you want to use, which I defined earlier. My args, oh, it is defined later on. So I am invoking this method generate data to generate x and y. So here global args is your my args in this. So this is having the dictionary like which scheme and which equation. So at present it is having Lex-Pedrock for on the Berger equation, Lex-Pedrock scheme on the Berger equation. Your dictionary is set with that argument. So now if you run this, you should be able to generate 10,000 samples using a scheme Lex-Pedrock. So technically it's like a random data with all one as a target. Now since I told you we are going from R2 to R, so our input neuron network should have 2 neurons, but since we are writing the code to make it efficient, we are calculating both the viscosity on the left interface and the right interface. So instead of 2 neurons, we are going to have 3 neurons in our input layer. Is it clear? So here you will get output also 2. So here you will have di plus half and di minus half in the output, so that you can run the pass the argument, 3 argument like 3 argument in neural network, and get both the left and right viscosity in one shot. So if you see here, your input layer has 3 neurons, 3 nodes. Then you have hidden layers, 1 hidden layer, 2, 3. 3 hidden layers are there in this FC1, FC2, FC3, and the FC4 is your fully connected, like from the last hidden layer to output layer. So 3 hidden layers are there, or two hidden layers are there. So you are having input layer 3, then in this hidden layer you have 64, then another hidden layer you have 64, and then another hidden layer. So total 64. So basically it's like kahan se lai? So you are having this kind of structure, 3 neuron, then 1 hidden layer with 64 neuron, another hidden layer with 64 neuron, then another hidden layer with 64 neuron, and then output layer with 2 neuron, which is giving you di plus half and d minus half. Clear? I am talking about the network architecture, and this is your the way we define the class. So you have a constructor, and then you are using the NN modules initialization constructor, and then how the information will pass. So your input vector x will pass through the first layer, and you are applying a ReLU activation function. So first you pass the input vector x in the first fully connected layer 1, FC1, then apply a ReLU nonlinear activity, then whatever output come, again you pass that to the fully connected layer 2 and again apply ReLU and one more time, and finally you are coming out. Okay, and once you define the class viscosity, you can define an object which is an instance of the class model. So when you, the moment you will execute this, you are having model object initialized. Okay, I can control zoom barabar zoom. Okay, so we have already generated the data. So I am using the train test split module of the scikit-learn, and I am giving my data and the target data x and y, and I am splitting it into test size 0.2, and again I am fixing the random seed 2. So then what will happen, this data set x and y will split into train data set, test data set, and train target and test target, and I am defining a batch size 64. So yesterday when I was talking about the gradient descent method, I said that stochastic gradient descent method is there. So basically when you try to decrease the loss, optimize the loss function on the entire data, it is computationally sometimes not possible. So people go with batch by batch. Okay, so PyTorch has the data loader where you can define the batch size. You can also write your own code that I am having this much data. First this 64 data will go, then another 64 data, another 64 data. But at the same time you have to initialize the randomization also to make the network generalized. So whatever you understand, it's okay. Whatever is not understanding, you go back and look into that machine learning. Then you can define the train loader. So whatever train data you got, you define, use the data loader utility of the PyTorch and define the train loader. So what it does, it take your data and it pre-process it in such a way that you can use directly it for the training purpose. So it will take care of your randomization, shuffling the data during the training. It will take care of the batch size during the training. Sometimes you may have 64 batch size, but last batch will not have 64. So it will take care of all those things. So it is an inbuilt functionality which is there in data loader of PyTorch. Then since we are talking about the loss and it's a regression problem, we are going to talk about MSC loss. MSC loss module or function is defined in engine NN, which is again PyTorch utility. And we were talking about the optimizer. So we are going to use Adam optimizer, and we can define the learning rate 0.001. Yesterday somebody was asking me one. So here it is 0.001. And then once everything is set, you have to train the network. So one time you will pass the entire data, you will get the output, you calculate the loss, then it is not good, then you have to again train it. So when you are doing again training, so you will go for next epoch. So one time all the data pass through the network, it is called epoch. So one epoch, two epoch, three epoch. How many epochs depending on the problem which you are solving. So you have to keep on passing the data iteratively, and same time decrease the loss, and to decrease the loss you are going to update the neural network's weight and biases, the parameter, using the backpropagation algorithm. Okay, so this optimizer or optim.adam will do all the things for you. Okay, it is easy, that's why I'm doing it. Difficult thing I don't do. Then here we are having the training loop. So as I said, you define your number of epochs. So I kept here 200. You can keep, let us do it for 20 epochs. 20 epochs. Then I am defining, I want to see how the loss is changing with each epoch. So I am defining here two lists, one for the train loss and one for the test loss. So list in the Python is a data type where you can store different values. and at different positions. Then you will use this for loop epoch in all the epoch, and I am putting the model into the train mode, that I want to train the model. Model dot train means now the PyTorch knows that you are trying to train the model. That means you will be using the gradients in the tensor which is stored there, and it will keep that information with you with it. So whenever it is going forward pass, it will keep the gradient information at each node with respect to entire computational graph. And I am going to put my loss is 0 initially, and then you take the data from the train loader one by one, and then you put here optimizer. You are setting here all the gradient in the default optimizer which you define should be equal to 0 with 0 gradient, and then you calculate the criteria. How you are calculating? First you are giving this input to the model, it will give you the output of the model. Then you are using target and this output in the criteria. Criteria is nothing but the MSC loss. MSC loss is predicted value minus target value, one whole square. So this is your criteria which you have defined here, MSC loss. So you are calculating here MSC loss, and once you do loss dot backward, basically loss dot backward will, what it will do, it will accumulate the gradient of the loss with respect to theta, the parameters, all the weight and biases. And when you say invoke this step optimizer dot step, it will do this gradient descent upgrade. In this step all your weights will get updated depending on the gradient of the loss and the learning rate. Then once you finish one epoch, I want to see the loss, so I am appending my list of running loss. Then once first epoch is over for the training, I will put my model into evaluation mode. That means I do not want weights to upgrade in this process, entire process. So it is evaluation mode, and here again I am going to use my test loader and I calculate the loss. And then once epoch is over, I will calculate my train loss, which is nothing but the accumulated running loss divided by the length of the train loader, and validation loss is also defined the similar way, and I can print these loss over the entire training period. So if I run this code, so since we have taken Lex Frederick data, so our loss is pretty low, and I think I should restart the session. Okay, anyway, let I think it is keeping the previous detail. So you can see that this is your curve. Your train loss is decreasing and validation loss is also decreasing. It's a nicely decreasing loss. Behavior is good. But when I am taking, so this is your actual predicted value of the viscosity, all one, and this is the predicted value by the neural network. How is it? Is it good or bad? Is it good or bad? So this is my, this line is my actual value, but my neural network is giving at different point different viscosity. It is good or bad? Deepak, bad only? Bad only? All are bad only. See, you look at this values also, na? You are approximating 1. Now tell me, it's bad or good? So you are always in the vicinity of 1 only, na? This is the effect of scaling. So if you keep your scale from 0.9 to 1, then you will say it's very good approximation. So sometimes you need to change your way of viewing the things also. So if I, so I think this is giving pretty good prediction of the viscosity for the Lexfetric case. Now I will use all these things for actual computation of the solution. So I am taking initial condition like sign or negative sign in the interval -1 to 1, and I am using a square shape initial condition also for the schemes. And here we are calculating the numerical viscosity. So some of the previously defined functions are being called here, and this is my PD solver. So this is the function which I am defining for solving the PD. So solve PD is a method. What it takes model, and it takes the configuration for which you want to learn, for which you want to learn this function or run this function, sorry. So if I am having configuration set as Lex-Federic or Lex-Vendrop as a numerical scheme, it will solve exact solution, it will give you. But if you put a neural network, it will give you the neural network. So basically run dot underscore config is a dictionary which contain all the information, the choice of the user. Okay, so we are discretizing the total domain into 100 grid points, and then you are defining delta x, then CFL is 0.5, and then I am defining the initial condition. Okay, so IC is the initial condition which we are going to pass. Initial IC contains the initial condition, choice of the initial condition, and when I invoke this method initial condition here, so depending on the initial condition choice, either you will get the initialized value of u as sin pi x or minus sin pi x or a square shape initial condition, and I am defining my final time t, and then we can have this while loop where you are marching in time, starting with the 0 initial condition and going up to the time t equal to final. So if you remember, I have h lambda. So basically here we are defining the h lambda. This fact is nothing but the h lambda fact, like as a factor. H lambda is lambda for the Lex-Federic scheme. I said I have defined earlier. It is there in the notebook also. In the Lex-Federic case, it is 1 by lambda, and otherwise it is default dt by dx. Lambda is always dt by dx. And then you are having, if your equation is in the dictionary run config with the key equation, if the value is linear, then you return the flux, linear flux f equal to u, otherwise you return the flux of Berger equation u square by 2. Then once you calculate this, you are going to get discrete values. So you are using f right and f left. So f right is so you are u is 1 2 3 4 f. So you write, so you are basically, this is your ui, and the ui right is ui plus 1. So you are going to start with 2 3 4, you are going to the next level, and the first element will come here. It's a cyclic permutation or rotation. Okay, and we are able to do this because all the initial condition which we have used, we can apply periodic boundary condition. So if you see the result towards the end, all the functions can be, all the problem can be solved using the periodic boundary condition. So we can use this. It has nothing with the machine learning. It is related with the scientific computing aspect, finite difference method. And similarly, you calculate u left because you need ui plus 1 and ui minus 1 in this. So now you can calculate the numerical viscosity, where for the computing numerical viscosity you need u and the configuration and the model also. Whether you will use model or not, that is a different thing. And I will run this. So once you calculate d, you can talk about the right interface flux fi plus half and left interface flux at fi minus half, and then you can update. So I will run it here. So all thing is set. Now let us see what are the configuration, what are the initial condition we are going to use. So I am taking my T final equal to 0.3, let us see, and I want my first initial condition as sine. So basically my initial condition is sine pi x, okay, and I have trained it for the linear problem, so I can use it for inference only when you are using solving for the linear problem. So I have already defined the top as a global, like what equation I am solving. So if you see, it is frozen here. It's for the Burger's equation type, okay, which I have defined here because of this one. So now I can use only for the Burger equation. So this is my configuration. So this is my first configuration where I am talking about I want to compute the solution with Lex-Fedorov scheme, and my method choice. So method choice is having three choices. One is Lex-Fedorov, one is Lex-Fedrick, and third one is neural network. So I am using for the scheme Lex-Fedorov. I am using method choice also Lex-Fedorov. Equation type as equation. IC we have defined T equal to T. This is a dictionary. So in the dictionary we are setting all the choices. So this is one configuration for the Lex-Fedorov scheme, configuration for the Lex-Fedrick scheme, and I am solving it. In this cell we are not using any neural network. So if you are taking this initial condition, so if you are taking this initial condition, the green one, you will see that because it's a Burger equation, because of the non-linearity, for the Burger equation, wave speed, the characteristic speed is same as u. So here your velocity of characteristic speed or wave speed is negative, so all the information will go to left, and here it is positive, so all the information will go to the right. So this is the result by the Lex-Fedorov scheme, which is red color, and this is the result by the Lex-Fedrick scheme, which is first order. So you can see if you actually compute the exact solution, it will come like this, straight line, like a triangle, sharp corner will be there. So basically that means all the method which we develop is working fine. In the second cell, we are going to compare the result with the neural network also. So you can, I have to change the size. So you can see that this is the solution by the exact neural network, sorry, Lex-Fedrick scheme, and the solution by neural network prediction is also overlapping on it. Let me check. Scheme choice is. So you can see that though we train the neural network on the Lex-Fedorov scheme data, but it is giving the result which is coming closer to Lex-Fedrick scheme. Now why it is happening? Because we saw that we are getting the approximation, but it is not exactly 1. So maybe that is one of the reason. If I change my equation type, let us see. If I take my negative sign, no, I will take third, square shape, and if I run there, so here we are getting the same. We have trained the network scheme choice is what? Scheme. So the data which we generated is by the Lex-Fedrick scheme, I think. Sorry, we generated the data with the Lex-Fedrick scheme. That's why our neural network is predicting the Lex-Fedrick viscosity. I thought it is with the Lex Van Drop. So let us do, so basically if now we are on the right position. So our this stepwise blue color is the exact Lex Frederick scheme, and the result obtained by the neural network. When neural network predict the viscosity, and when we use that viscosity in the Lex Frederick scheme, we are getting the result closer to the exact Lex Frederick scheme, and Lex Van Drop is giving you oscillation here. Okay. Now let us do this same thing with the Lex Van Drop scheme. So I will write here scheme choice as 1 for the Berger equation, and if I run all, after some time you will see that your neural network is able to predict the viscosity, numerical viscosity, which is very much close to the numerical viscosity of no, so now you can see the black dotted one is the exact Lex Van Drop scheme solution, and this is the result obtained by the neural network. So we have a very nice agreement with this. Okay. So neural network can learn. Okay, but there is a problem with the generalization. Like if you want to solve the linear differential equation or transport equation, you have to again train the neural network. If you want to solve Berger equation, again you have to train. So you cannot train a model which can work for all the equation. This is one problem with the neural networks. So it can, so personally I don't use physics informed neural network approach. I don't work with that, because I feel that there is a lot of mathematical rigor already done by many mathematicians for centuries. So you have method, you try to improve the method without losing the mathematical property. For example, you can define you can use the neural network to make certain things better in the classical approach. For example, in numerical method for hyperbolic conjugation laws, we have essentially non-oscillatory reconstruction. So there it's a like iterative process to find out a smooth stencil. So that is a time consuming process. But if you do that, you have lot of mathematical property about stability, accuracy. Neural network you train, but you cannot prove that it is order of delta x to h to power 4, this approximation. It is giving good result which is eye pleasing, but it may not be satisfying the scientific accuracy requirement. So I personally believe that you use the neural network without changing the framework of the scientific computing. You just make some of the steps automated faster with the neural network. So for example, you can develop a shock detector. People are working on it. So they are developing neural network which can detect the discontinuity in the data, and then they are using the same classical scheme with little bit tweaking. So results are improving. So they don't have to really worry about the existence and convergence of the method. So this is one notebook. So I can share with you. This is what I promised yesterday, and the second problem which Professor Gowda asked, that equation. Shall I show the code? So that equation we have to write here. Professor Gowda will the equation which he discussed in morning session about oil recovery process.
Point is half. So 1 if, no, no, 0 less than x less than half, 0 if x is greater than half and less than 1. Okay. So now we will remove the layer here. Then what happens? Water will come down and oil moves this side. After some time, oil will be above and water will be in the down. Half of it shares. So while moving, how it moves? This is a center point half. It moves like here. Okay. In the beginning, it will go here, like here. It passes through the half. The water droplet here, this does not move like to the left or right side. It same remains, and only other water will go. Water will come this side, and this will go this side. Okay. So after some time, water will be in the down, and the oil will be in the up. So the model I explained to you is f of u is equal to u into 1 minus u. I explained why this model is coming. So that he does this now is numerical setup. Okay.
So this is the problem. So since there was not much time, so I used large language model and took its help to solve this problem. Okay, and since now we know what is Lex-Frederick scheme and not Lex-Van scheme, we will discuss these two schemes, how the solution is coming for these two schemes, and then we will see something which is very nice to observe. I am sure many of us do not know it. So here we are defining the domain of the problem from 0 to 1, and up to what time? Up to time t equal to 2 we will be looking into the solution. Nx is the number of grid point in the discretized special grid point. Then delta x is the variable which contains all the grid point values, and I am using the Lex-Frederick method. Here I am using time stepping using the CFL condition, and we are defining here flux. So f is u into 1 minus u, and its derivative is 1 minus 2u, and here I am using MATLAB's inline function facility. Okay, so you don't have to define a function like flux, you can do the inline function because it's a one line, and then this is the figure. Now we are having this solution update. So from n equal to 1 to nt is the final time step, number of steps in time domain, and we are marching by swapping. So we will take in the variable u old the initial condition u, and then we'll keep on updating this u. So every time we update and push it back to the u old, like this. You took this, calculate this solution, then you store this solution into this variable, again calculate the new one. So we are just marching. It's called marching with swapping. So just keep on swiping the old value, the last value, into the right hand side. So if I run with the Lex-Frederick method, sorry, I have to write this. So you can see this solution is coming like this. If I go with the t equal to 3, so we have time, another 10 minutes are there for this session. So I'll run it for 20 so that they can keep on watching it. So basically on the right side of this line is oil, on the left side of this line is water, and it will keep on moving. I don't know up to what time. It moved. No, it's So Lex fatigue scheme is giving this solution. But there are a lot of things which are happening here. How we are dealing with the, in this case, I have to train it actually. It will give, because we saw it working for the Lex fatigue scheme. So basically just viscosity we are learning from the neural network. We are not changing the scheme. So it will be, it is working like this. I think it is okay. Oh, I cancelled it. So Lex fatigue scheme is able to give you the desired result. Are you able to follow what I am saying? It's okay. There is no oil, no water, only simulation. So we'll go for a tea break, and after that, this is hands-on only, bhaiya. What hands-on? You will be talking about some theoretical Riemann problem, no? See, this is the result by Lex-Van Dorp scheme, and it is like this only till you die. It will be like this. Why? So that's why I say that always theoreticians enjoy. This is the result by Lex-Van Dorp scheme. It is going on. I don't know. I think I should keep it for 2. But if I take this 0, if I remove this initial condition 0, what will happen? See, if I make it 0.5, so before I discuss this, let us see my notebook. So I have discussed this initial condition. U is 1 if mod 1 by 3 is mod x is less than 1 by 3, otherwise it is 0 in this domain. This is my initial condition. 0 till mod x is less than 1 by 3, it is 1. When it is not, it is 0. I will take it, this initial condition I will change. I will change it to -1. This is the result which we got. So this is my initial condition. This is also the result obtained by the Lex-Van Dorp scheme. This is the result by Lex fatigue scheme. Okay. So why it is happening? Because in this initial condition, your wave speed goes to 0. This initial condition has a expansive sonic point, a point where the wave speed changes. So in Berger equation, I said that your wave speed is nothing but the value u itself. So here your value of u is -1, up to here value is 1. When you use wave speed calculation, u r plus ul divided by 2. So 1 minus 1 divided by 2 equal to 0. So your flux will become only this Fi plus half 1 by 2 Fi plus 1 plus 0 times this. So there is no viscosity numerically at this point, and because of that your profile will not move in this direction, and here also it is 0, but it is a compressive. This is your expansive sonic point. So what is happening? The left hand discontinuity is getting a fan shape, it's spreading, but the right hand side discontinuity, because it's with the entropy inequality, you can show that this is a shock. If you go by the method of characteristic, you can see that the characteristics are impinging into the characteristic curve. So this will anyway not moving. In the Lex fatigue scheme, you can see that is a stepwise approximation, because Lex fatigue scheme is over diffusive, but Lex Van Dorp scheme is not going to do anything for this kind of thing, because wave speed becomes 0. So when wave speed becomes 0, scheme is not having any marching property. So same kind of thing is happening here also. If I am taking 0 with Lex van 't Hoff scheme, nothing will move, because in this case your wave speed is 1 minus 2u. So at u equal to 0.5, 1 minus 2 into 0.5, your wave speed is becoming 0. So Lex van 't Hoff scheme will stay ideal. It will take it as a stationary solution. It won't give any dynamics to you. So with this I am done. Sir, anything you? Okay. Any question from anybody? No question? Anybody from online? Any question? Then otherwise I will. You have one question, yes. See, Gaussian, my idea was that I want to choose the data between interval -1 to 1. So that's why I used uniform distribution. If you take if you sample from the Gaussian distribution with mean 0 and variance 1, there is no guarantee that your data is coming between -1 to 1. It can go a little bit beyond also. So again, you have to do the rescaling, standardization of the data. So that's why. Because standardization is always a practice. It's called data cleaning. So during the sampling itself, I am taking care of that. Any other question? What is there with T? Huh? Okay, thank you for listening and bearing with me. Yeah, from online, anybody want to ask anything? If not, let us thank Professor Ritesh Kumar Dubey for his valuable lecture. And I request Professor Gowda to hand over a memento to Professor Dubey. Memento? Yes. For me also? This is good. Professor Gowda? Gowda, sir? Another topic. No, you take that one. You just take this. Oh, okay. This one alone. Fine. Thank you. It's my pleasure to meet you today. I know him from his student days. So we are friends from his student days. Like so almost nice. 20 years. 20 years? Okay, fine. Almost. Thank you. Yeah? Okay, thank you. Now we will go for tea break. Once again we will come back. Thank you, boss.